trained, do you think that the model could use the inventing artifacts in some way that furthers the training?
Yeah, that's a great question. This is often a problem with using a machine learned model to create data for you, because there's always going to be an artifact, and the model will not learn the real task. It'll just learn to represent the artifact. And so to get away from this, what we do is we take the in-painted image and we add further noise to it. And then we use a diffusion model to denoise the image. And when that diffusion model denoises the image, it tends to remove the noise that you added, and it tends to remove the noise that your in-painting generated. Essentially, you can think of this as more serious data augmentation in order to modify the image. If you have corruptions, you can either remove them or you can add corruptions everywhere. It's like, it's like the old tales that we've heard as kids. So that helps a lot.
Thank you.
One last question. Have you done any updation in kind of comparing a lot of these approaches that you showed with real data? Because we always know that the domain gap for synthetic data is a big bottleneck of using them, especially when you can collect real data. For any of the proposed techniques or methods that you've shown, do you have any thoughts on how effective they are when comparing with cases where you can actually get real data?
So in robotics, we have, collecting real data is extremely slow. And so if you want to train a navigation policy on real data, you can collect about 100 episodes, at least, unless you're Google, who can spend 17 months. And so when you look at 100 episodes and do imitation learning, we have done this, and you get extremely poor results. So I would say that in extreme data scarce regimes, we have tried this, and it's not even worth putting as a baseline because it just doesn't work.
QA or video QA that you showed toward the end?
Yeah, so the thing that I showed at the end for image QA or video QA is only for benchmarking. In those domains, there is enough real data. And so I don't think we have been very successful at using synthetic data for a lot of image tasks. It's only these sort of out of the ordinary image tasks, like the one I was describing about, missing people and missing chairs. Those are the tasks where synthetic data can help. When it comes to image parsing, there's enough data where synthetic data, I don't think, has too many benefits.
Because you can create data to solve that specific task, but if you want to train generic model that can solve many tasks, then you also need to figure out how to combine that data with real data.
Yes.
Different tasks.
Yes.
Really
yes. I think what you're suggesting is, well, let's say I want to answer a particular question and the model does poorly in benchmarking. Then why not generate that data in synthetic data and add it to real world data and then see if that number goes up? Well, the mantra that we have is we really love synthetic data. But if you train with synthetic data, you have to test on real data. And so in this like dynamic generation framework, we'll have to have a few tests to make sure that dynamically generating training data can still let you do simple real transfer. So yeah, great point. Okay, thank you.
Thank you.
Sorry for the interruption. All right, we continue. All right, so we talk about we are living in an exciting era of data-driven revolution, where all these different forms of data actually brought a lot of exciting new opportunity to AI and machine learning. In my view, as somebody who has, VR, AR, robotics and computer graphics background, I see all these data provide us in many ways an ability to reconstruct and also synthesize, and even better yet, predict all kind of events, all kind of structure, all type of a dynamical phenomenon. And if you think about it, that's exactly what convolutional neural network does, is it allows us to take samples, data, to reconstruct, to predict the signals. And that's what I'm going to talk about today. That is, we could do it in a really interesting way as we move forward. So the vision, at least from a personal view, for the future trend in computing is we are trying to create this ultimate metaverse, which is going to transcend the boundary between the physical world we live in and the virtual world, the digital world that we work with. And so in order to do that, we need to bring the real world into the metaverse. That means to bring the physical world into the metaverse. That means we have to recreate it. And this will enable us to do what is previously for many, many decades not possible. That is predict how the system evolved and how the future events may happen. It also allows us to have a virtual playground and a meta labs for testing, evaluations, designing, verifying, validating, and prototyping. Now, this, by the way, by no means is anything new. We have been doing this across different communities for many years, from geometric reconstruction, scene reconstruction in both computer graphics and computer vision community, to image and video reconstruction, photorealistic reconstruction, you name it, the most recently NERF, motion reconstructions, motion control, more recently reinforcement learning, and now we want to take how humans move into teaching how the robot moves. So it's creating tons of excitement in robotics, in vision, and in many other areas. We also are increasingly become very interested in creating avatars. That is us. At the end of the day, I like to think what we are doing is to not create a universe of machine, but to create all these exciting new technology that's going to augment us. So I like to think we are the center of the universe. So what we want to do is to create a human-centered systems or human-centered autonomy. Now, I am also working in, I'm also an Amazon scholar, so I work in Amazon, and the group I'm with is Virtual Try-On. So we are also very interested in reconstruct garments. And when we talk about garment, we cannot just talk about the geometry, we also need to talk about the fabric and the physical property associated with it. So what are the data challenges? Well, the data challenges that we are facing is the diversity of data representation, as I already highlighted, from 2D, 3D to high dimensional space, but also the type of data, whether it's text, number, images, audio, videos, or abstract informations. But what is more interesting is we have this real world challenge, which is the geometry, the physics, the appearance, the behaviors, and the functionality of all these different entities around us. What is really not talked about a lot, which I know is hitting me and hitting my research group, and in fact, I know it's hitting a lot of places. Most of people just don't talk about this, is the volume of the data and the associated computation. The heat cooling, you don't worry about it because air conditioned. But someone is paying for that electricity bill and the storage, the memory. So I'm hoping through this, I'm going to talk about synthetic data generation today, but I hope that we will also start to think about how can we do synthetic data generation in a more intelligent way. So there's also other thing which is being introduced by data is the biases, the noises, the uncertainty, and the incompleteness of the data. And that's where synthetic data come in, is to fill in the gap of that missing data that we are able to capture from the real world. And what's even more interesting that we don't think a lot about is the taxonomy of all different object and scene and ontology and the categorization of all these things that we are trying to process visually, contextually, or for any of the application. And ultimately, a lot of time we capture data, we don't have a context, or we don't exactly have a control capturing process. And those are all some of the reason that contribute to the data problem. So what does this mean when we have all these challenges in data? Well, technically, we have some challenges from the technical side as well. This means a lot of generative AI technique and data-driven methods often lacks, it offers empirical model. And a lot of time the black box results are not always interpretable and explainable. It's also limited to a very incomplete subset of the observation. It's not a complete set of. And what this ultimately means is that the results that we learn are not necessarily generalizable to unseen domain and scenarios. They don't always transfer across different tasks. People talk about, oh, it's transferable, it's generalization, it's generalizable. Oh, it's just because you walk on different surfaces. As a robotics person, I look at it, I say, it's a flat surface. It doesn't matter what kind of surfaces you walk on. It's flat surfaces. It's the same domain. And so these are the kind of things that we need to really think about. What is really different when it's cross-domain? Is your environment completely different? You have more obstacles. Even worse yet, obstacle that's moving constantly, like your pedestrian crossing, like your animal just running out there in the middle of a road. And so most of these autonomous systems are not robust to either input or domain variation. And learning purely from data is extremely costly. It is very, very costly. Okay, so I do want to come back before I go on and talk about simulation. I want to mention one thing and define one thing, and that is model. What is a model? I like to say that a lot of physics that we know about, whether it's rigid, deformable, articulated, you name it, human body, multiple flows, they were all derived using observed major data. Geometric model that we have in the 3D world, they were all captured directly from observed and major data over many, many centuries and decades. They are object, scene, environment, human, inanimate, and behavioral functional model that we know, again, they were all recorded from the sample instance. So I am hoping that this is going to remind us what I'm about to talk about of the 3 different domains or 3 different subtopic area. First one, I'm going to talk about autonomous driving. This is an area which my group has worked on quite a bit, but also our experiences in virtual try-on and how we use data. And I'll also address a combination of a synthetic data combined with the real world data. But last but not least is addressing the robustness and generalization problems. So for autonomous driving, there are plenty of companies out there capturing all kind of data, having a real driver driving that. So we are not interested in doing that. So where does the data come in? Well, we are looking at scenarios that are difficult to capture, which is the accidental scenario, pre-crash scenario, rare event scenarios. So we are doing this but basically, instead of having a human driver, we are not going to put any human driver in danger. We're not going to put any pedestrian in danger. We certainly are not going to set loose a whole bunch of animals running on the highway and try to cause accidents. That is not what we want to do. What we want to do is to simulate all these scenarios. And so our goal is to develop an end-to-end control policy that can model the temporal sequences and process the input from a single front-facing camera to perform normal driving and also collision avoidance. So what do we do? Well, we basically parameterize our environment setting, grounded directly from the transportation engineering and accident analysis studies over decades. And these analyses tell us what are the different kind of scenarios that you can run into collisions. And basically it categorizes pre-crash scenarios. We also develop what we call a probabilistic multi-agent simulation, which is based on a multi-agent collision avoidance that is based on probabilistic approach. I will not go into the detail about this approach. If you're interested, you can email me, and the library is also on the web. And then what we did is we use a memory-enabled control policy that use a combination of CNN and LSTM. We use CNN to extract image feature directly from the RGB images. And then we use those image features to track over time and learn the temporal dynamics through LSTM and memorizing it in a way that what the dynamics will be. So overall, this is our system where we actually have a simulation module that will look into a literature and then simulate all these accident scenario. When we did this work, we did it manually. Today, with large language model, we could easily move toward that direction where we can actually do a text conversion to simulation. We also assume we actually have the real world road network, in which we do. There are plenty of sources available, and we use that as the basis. So we are not simulating out of nowhere and hallucinating. We are simulating on the real world road network. Then we perform all these simulation. We look at where the accident occurred. Because we are running a simulation, the simulation is able to annotate where the accident occurred. So this allowed the controller to go back and roll back in time to determine how would changing any one of the action might actually affect. And then all these data are being inputted into our control policy network that will learn how to learn these scenarios directly from the simulated accident data. And this just kind of give you some idea that basically we have these poles in the highway, we have different kind of weather conditions, and we have obstacles. We record the trajectory. We actually have the system do the trajectory analysis, and directly from the accidents, we know where we alter the trajectory can actually avoid the obstacles. So this is basically a visualization of what's going on, varying different trajectory and figuring out how you can avoid these obstacles right here. This is all done automatically, and no human in the loop. And we use this architecture, as I already mentioned, to deal with the kind of input images that we collect. Sorry. So this is a very, very simple scenarios where we literally have the car running into the pole directly, and we are using a standard driving simulator. This one that we use was from NVIDIA. We have also used Kala, and we have used several other simulators that we have tested. Now, with the standard approach, you would run straight to the pole, no matter how many times you have the accident. With ours, you actually learn how to avoid it. I'm just going to roll all the way to the end, and just to show you that even if you teach it a little bit better how to avoid the obstacle, the car will eventually kind of skid through to the outside. And so this particular approach actually generated a far better, safer trajectory compared to a brute force approach using the existing network. I'm going to roll this a little bit. And we have also tested this on different weather condition and also different lighting condition as well, using the similar kind of approach. You won't hear the sound, but there's actually a little bit of raining sound as well. But we have gone further by using what I just mentioned, that reports that was recorded and reported by the National Highway Transportation and Safety Agency. These are different scenarios that we have simulated. And we have actually learned directly from these different sets of scenario. But one thing that I do want to mention was, it's not in my slides, but the future of autonomous driving is not going to be auto autonomous driving car. I am sure many of you drive today, you will continue to drive in the next 10, 20 years. So one of the things that we continue to build on top of this is that we are actually building a virtual reality simulator that are coupled together with a driving simulator and a large-scale traffic simulation, but we put a real human subject in there. We have hundreds of human driver drive through our simulated car in this large-scale urban environment. Why do we do that? Safety. We put them through all these same sets of scenario. We're trying to collect how human driver respond. And we are in the process of collecting and hoping to release that data set for other people to learn. Because the challenge of an autonomous vehicle, as I already mentioned, is always dealing with a mixed autonomy environment. That is, it's not an autonomous system we worry about. It's the other human factor, the pedestrian, the animals. And so how does other human driver respond to the environment, and thereby your car, your autonomous car, will need to respond to them. So imagine on a highway, right nearby you are all these human drivers. They respond differently to different scenarios. Your car, your autonomous car, need to be able to predict how they might maneuver. And so that is another kind of data that we need to capture. All right, so that was sort of a detour, but that kind of tell you that simulated data have a lot of values, because it also allows us to create a simulation environment to collect actively user feedback. So these different scenarios that we created in VR environment, we can use them to collect real driver and how they drive. Now, we actually also, there was a question about transfer learning, and this keep popping up, does the simulated data actually offer you ability to transfer learned for, say, autonomous vehicle? What we actually found is yes. We have learning just purely based on simulated data. We also have learning that was trained purely based on real world data. We have one that used a combination of both. And what we have found was the learning that we learn from simulated data does indeed transfer to a combination of both. Where it really shines is on situation that we don't have the real world data, and that is the accident data. So it does improve the general driving behaviors, and also it reduces the number of collision. All right, so I won't go into all the detail. We have done a lot of data that actually capture that. And these are sort of some of the simulated accidents. Okay, so those are some of the example. And you're gonna say, well, they don't look great. We actually have found when people are engaged, the graphics doesn't have to be perfect. And we have done a user study. The differences of the rendering and the visual fidelity only affect about 20 to 25% of the results in terms of effectiveness in learning. Now, we are also in the process of automatically converting our simulated videos into photorealistic, so it's a style transfer. And we are in the process of assessing how much that really helped the transfer learning. We don't know yet. All right, so that kind of give you some idea. And this is some of the latest work that we have done on hybrid traffic simulation, where we actually combine a large number of traffic model. Actually, we are able to simulate urban traffic at scale that basically combine a microscopic simulation of simulating individual car, but also a macro simulation that simulated traffic flow. And we use it for flow prediction, as well as traffic control. And one of the common tasks in traffic engineering is if you have a car in front that's driving really slow, it actually control the traffic speed. So those are, and we also have validate our simulation results against the real world capture result. So the conclusion on the first part for autonomous driving is that we found simulated data to complement the real world data. And we also found that transfer learning can help to overcome the lack of real world data on these corner cases, rare events, and accidental scenarios. And the simulated data offer us automatically label and annotated data that you don't actually need to have the human in the loop to do that. We see that training of an autonomous vehicle or self-driving car can use transfer learning with this combination of both simulated data and real world capture data. Now, moving forward, I'm going to talk a bit about virtual try-on. And so, you know, the whole idea of virtual try-on is that you can shop online and you can try on the clothes with just your photographs. And one of the important thing that to do that, you need to have your body reconstructed from a single view images or a couple view. Then you also need to estimate automatically from the image-based data, because most of the time that's all you have. it's not a scalable solution to actually go to the lab and capture the fabric material information of every single fabric that you can buy online. So we are looking at image-based parameter estimation for the material. And we are also looking at image-based reconstruction of the garment. And lastly, we want to be able to render that fitting information, how a garment look on your body automatically in real time back to you. And so to do this, we borrow synthetic data, different kind of synthetic data, and which I'm going to talk about just a minute. So first of all, we are using a shape-aware human pose and shape reconstruction using a multi-view images. This basic idea here is we could do better than a single view. If we have 2 view or 3 view, we can do even better. And what we want is we want an arbitrary multi-view learning framework that can learn from any numbers of images. You can accept 1, but also 2 or 3. Depending on the correlation of the images and also the angle, more is not always better. It's really the information you get from each view. Now, we have also created very large synthetic data sets that we have the ground truth parameters, which could be your camera locations, your fabric materials, and so on, and with the clothed human body, where even a human body can be synthetically generated, so we can verify. Now, our key contribution here is, as I already mentioned, which is a large data sets of synthetic data with ground truth parameters for verification and validations, but also we use it for training. And also we have the scalable framework. So very quickly, how does this work? Well, here's a perfect example of our network. It's basically a cascading of regression network. Each one of them is for each single view. And the parameters of the body shape is shared across multiple view because it's the same body, the same poses. They don't have to be in the same poses, but they do have to be the same body. They can be captured from each one. Then we share the camera poses information and angle down each horizontally because that is the same across each view. But the human parameter are shared across different views. And so those are some of the information that we share, okay? In terms of cascading down this way across different view or down the streams for this multi-stage processing through each their network. We created a very large synthetic data set where we use the CMU MoCA data set, and we create basically a uniform shape variation. We basically sample all different parameters. We use a simple model, which is a parametric model based on capturing of thousands of real world human body to create this parametric model. So we systematically vary the parameters to create large body of sample this way, synthetic body. Then we also create all kind of clothes. And we also download a whole bunch of images of all different type and all different lighting, and we render them and we simulate them. This was a very, very complex data generation, as you could see. Motion, shape, clothes, and rendering, lighting condition. So with all these data sets, we create a synthetic data set for training. What we have found was that the synthetic data sets with that, we were able to outperform the same training system without. And the data is shown there. And I hope that convinced you that the synthetic data does improve. We also compare against all the others. Now, this is using the multi-view, and it also outperform all the other state-of-art approach as well. I do want to highlight where we really win. We really win on the extremal cases. Why? Because typically the real-world data capturing don't capture the extremal data, which are people who are not in your typical normal distribution. And I hope that should be statistically very obvious. So people who are extremely skinny, people who are big and tall, or small and petite, very small and petite, those don't get captured very well in your normal data capturing. Those people benefit the most. And from the Amazon perspective, those are our customers that we love to have. Because imagine how much difficulty they have shopping, and we can help them. And we think this is a way of democratizing shopping. And we have more comparison, as you can see. So even very curvy bodies benefit tremendously. So all these, extremal shape, extremal height, weight, all benefit. So I want to summarize here, at least through this, what we are offering is a synthetic data generation pipeline that enable direct shape supervision through this process of generating all kind of data for the human body. But we also account for out of distribution samples. That's a very important things. And we still have all the other shape parameters that we have captured already embedded in the shape-aware parametric model. And we are also able to capture difficult settings. Poor lighting, that's important. Different kind of environment, dynamic environment, so you name it. And also motion. Now we have, take the same approach and move on and talk about and think about the garment material. This is other really important things. You can shop if the fabric material is not exactly what you wanted. Just kind of die. Can you hear me? You'll be back? Okay. All right. So what we did is we generate label video data using physics-based simulation. And again, this is the cases where we actually have used real-world data. There was a large data set that was captured at MIT. You hang a clothes and you let the wind blow, or you apply the forces, you apply sun, and you see how the clothes move and how they wrinkle for different fabric material. It's all great, but it's a very controlled experiment. It's limited in terms of the data source availability. So how do you really generate a large variation of synthetic data for all different fabric material? It's very hard. So the only way to do that, again, is by varying the parameters directly. And that's basically what we did. But we were able to do way beyond hanging clothes. We have also able to simulate bending. And the bending motions are very common because as human, our articulated body, we move. Our arm moves, we bend. Our legs move, it bends. And so these are the bending motions and just sort of hanging motion. So we have introduced these two settings where we have different kind of motion, a bending motion and just straight hanging motion. We have also tested simulation with different meshes. Mesh resolution affect your simulation outcome. For those of you who don't work in simulation, you know that it matters. So when you run the simulation, you want to check that. We also run it on different texture. Texture, again, affect the visual perception. And we also change the camera positions. Now, we use RSIM, and it allows us to easily control all different kind of condition, lighting, external forces, and so on. So we are, again, able to generate a large number of label data this way. We run it against, various type of a parameter variation. And what we found is we compare against either CNN alone or LSTM alone, or using our network, our still with all these different variation, our perform the best. And we compare against the state of art. Again, it outperformed the other by a very significant margin there. Now, I'll just kind of show you really quickly what the simulation result look like. So this is some of the training data that we have generated synthetically. On the left are synthetic data. On the right is our predicted material property. And you can see the network doesn't know what's synthetic, what's real. It just treats every single video as input. This on the left is the real world capture data from MIT. On the right is our reconstructed material using our network and also our animation by applying the same forces. We also show that the real world material can be cloned on a simulated animated fabric or a skirt in this particular case. And silk and the stiffer material, you can see the differences on how the skirt flow as the wind blow. So I hope that kind of give you some idea where synthetic data can, in fact, be able to teach the machine learning, the dynamics and the material property. So lesson number 2 learned is that By using simulated and synthetic data, we can account for various lighting, effect, camera poses, and also we can simulate different environments, but also external forces, varying external forces, motion effect, and so on. But it also, very importantly, provide a verification and a validation framework, because we know the exact parameters and the ground truth data is known in our data sets, in the simulators. So we can always test all the other approach with these data sets. And it provides an automatic supervision without a laborious data labeling. You don't have to go in and annotate and segment it. And I like to say that we talk about the large language model era, and most of the people don't recognize. In fact, one of the reasons large language model, VLM working so well, when you have vision and your language model, they work so well, is because language is a label. It came automatically with the images and the videos. That is a label, except we don't do it. Someone else has already have done it. So that the data labeling of the coupling between language and images is what makes it so powerful. With simulation, it can achieve the same. All right, so we go on and extending that work a little bit by using not just, trying to figure out what the material is, we are also trying to do a joint estimation of the human body and the garment. We're interested in the geometry now. So we're not just looking at the material, we are also looking at the garment. So we do this by, again, an end-to-end neural network with a fabric material, using a very similar kind of network I already mentioned, but we are also using a 2-level autoencoder for the garment geometry. So basically what we're doing is we're trying to capture, without going into all the detail, the global shape of the garment and the local patches of the garment. And the local patches of garment give you the detail that still preserved the material property, and the global patches, the global shape give you the global constraint. So that's the basic idea, okay? I won't go into all the detail on the network, but you will see that we are taking any RGB videos and using CNN, extract the image features, coupled together with the body estimation and the garment estimation. We actually use the garment latent code directly from the image feature, the body we know, and we send it through, combine both of them. We are able to extract the garment meshes and also the fabric material, but at the same time, also the human body. Again, I won't go into all the detail, but it's important to know that this kind of framework generalizes pretty much the same as I already mentioned for the texture, except now we are able to go a step further by using this 2-level encoder decoder to get the geometry as well. And these are just sort of some of the scenario that was simulated and rendered using our network. Using our synthetic data generation pipeline to create the training data. And, we are using both the real world and synthetic data, and the accuracy is the highest using our approach. We didn't just stop there. We actually also perform a visual perception user study. We literally have the ground truth on the top and the predicted results on the bottom, and we ask the user to rank. And with the user input, we were able to see very, very high, perceptual results, where 0 is distinct, they're different, 10 is identical, 5 is similar, somewhere in between, and almost every single one of these, it's way above 5. It's like 6, 7, 8. So fairly good. Qualitative result, here are some of the reconstructed qualitative result, as you can see. And the most important thing is a lot of time, the real test is in the pudding. You need to try it on unseen real world video that you did not simulate. So we tried it on the real world simulation. On the real world video data, and you saw that. Those are little blue patches that capturing all the local patches, and it's like learning and training at the same time. It's able to reconstruct the poses and the geometry. We have also done the material transfer, where we have the video input on the left, and that's our training videos, and we were able to recover that. I'm sorry, that's not a training video, that's a test videos on the left, and And then on the right is our chrome material that we were able to predict using our network. And as you see, as the material gets stiffer and stiffer and stiffer, the cloth also change its shape due to the material. That was simulation. This is real world. This is actually one of my colleagues at Amazon. He was our model. And so we have him capture the video at home, completely uncontrolled condition. He captured the video for us and we run it and tested. And we were able to basically reconstruct what you see, the fabric material for the t-shirts and so on, and the garment. And we have actually used this approach for, again, a real world input videos to be able to reconstruct the videos from the left and recreate the body and then be able to get the fabric material. The rendering is where we still need some more work, and we are actually working on that, on combining nerve into some of these framework. So summary is that the synthetic and simulated data generate all these different lighting effect, camera poses, and different environment and interactions. And you know, again, it provides about verification validation. I want to go very quickly because I realize I'm going to be running out of time due to all the technical difficulty. One last thing I did want to mention is the realistic garment draping and prediction. We actually developed a learning framework. It's a semi-supervised learning framework where all the training data are simulated. They are all from Claude Simulator. And essentially, we use a physics simulation to estimate the body, all synthetic data, cloth dynamics. Everything is all simulated data. We learn the dynamics, and we were able to use this learned network, be able to predict how the cloth will drape on various bodies, all different kind of bodies, real world customer body, and test it on, and we use physics enforced optimization to encode some of these physics constraints, like no penetrations. We can change adaptively the material because this was for people to buy t-shirt online with the graphics design being printed. And so when you print the graphic design, the material, your cloth change. So this, we don't have any control, but with our approach, the fabric will automatically adapt to those material changes. What we found was very interestingly, it's 1,000 times speed up if we do it this way, by comparing it, you know, to a pure simulation-based approach. These are the simulated and the learned outcome using this dynamics driven learn model for predicting how the t-shirt will look. The design you see are graphics design. They are actually printed material onto the t-shirt. So you actually change the fabric depending on where you print. Our goal is to show you that whether it's a small or medium or large, doesn't matter. You know how you will look on your body based on your photograph as input. And that was the goal. That is to help you shopping. Okay. And just very quickly, if I can play these videos. Is that with this, we can actually also animate and move, and you can see how the t-shirt wrinkles and how the graphics move along with that body in motion. Okay, so this is a perfect example where we actually can learn very complex cloth dynamics directly from simulated data. We did not capture any real world data to do this because it was simply not possible. We would have to capture all kind of fabric, all kind of garments, and so on. Simulation was the only way to go. Okay, so I hope through the previous talk and here, you can see where simulated data or synthetic data can really fill in the gap. It's filling the gap where it's not possible to capture all those kind of scenarios. Now, lastly, I want to talk about this very, very quickly, which is regarding robustness and generalization. So one of the things that we have seen a lot is that a lot of autonomous driving and a lot of vision-enabled systems and augmented system all use RGB data. The fact is, when you have a car driving in the environment, any kind of natural environment, there's going to be natural lighting effect variation. We actually done some study. The change of lighting does affect how the vision module process the results. So Simple example, this was a little bird called goldfinch. Well, different kind of image corruption produce different results. And this is the problem that the vision community has to deal with. What's the typical solution? Well, as you can see, right? Very simple example. Now, this is what an autonomous system, autonomous self-driving car had to deal with. Same front images for different conditions, snow, frost, fog. Typically, the data collected is, sunny California, Arizona, sunny, very few people, no snow, no fog. You do have to deal with this. So these are image corruption and zoom blur, motion blur, pixelation, JPEG, you name it, all kind and distortion. So how do we deal with this? Well, we actually had a paper in Europe 2021 where, and also in the robotic conference, the approaches are very similar in philosophy, but different, which is we use the approach are similar in the sense that we use adversarial training. And it's basically using a min-max optimization process. You have an input data comes in, you have a model. It doesn't matter what that model is. It's well known, this kind of concept is that you can actually add adversarial perturbation to your system and you can train it with it. You update a parameter accordingly. And so that's basically what we did. In the inner loop, you want to maximize all kind of perturbation on the system. And in the outer loop, you basically want to find what's the parameter that can cause your maximum perturbation. And in the outer loop, you want to minimize the impact on your training process and maximize your accuracy. So those are the kind of framework that we did. And what we need to do is to do what's called data augmentation in the machine learning community. What that really means is if we do this, we can do it two-way. We can perturb the input images through the image attribute, which will including the color, the intensity values, the hues, and noises, and so on. Those are the image attribute. The other way is to perturb the geometry. And we have just perturb straight on the images because we were thinking about natural degradation. Now, what was really interesting is we perturb each one of the axes independently through what we call the sensitivity analysis. And I'm going to define that in just a minute. The sensitivity analysis basically say, if I vary my input, how does my output change? And we don't care what's the black box in between. But sensitivity analysis allow us to know how the system will react under different conditions. If you do it this way, it is, however, very expensive because it means that you have to sample the whole kind of an input variation to get all kind of output variation. We did this for all the image attribute. We don't know it's an end-to-end driving system. So we actually don't know where is the visual, where is the planning, where is the control. We just simply do it on the input and the output. And we study that. It does help improve the robustness, and it also help the overall training of the systems. So what we have proposed is a general data augmentation framework using simulated perturbation. So we are purposely generating perturbation to the image attribute to generate all these corrupted data, and we trained it on all kind of corruption. Now, that was basically what we have. So we did the transfer learning from sim to sim and sim to real, and it works. And one thing that, however, I just want to say was that we found this approach, even though effective, we're doing data augmentation. Like any one of you who have worked with data augmentation, you know it's very expensive, right? So that is not a responsible computing. And so for most recently, we've been looking at how can we do this? So we have this pipeline where we have the vanilla training, then we perform the sensitivity analysis, and we try to see what are the perturbations that are going to give us the maximum deviation. And then we try to weight the sample and then train it with repeat. Now, sensitivity analysis, as I already mentioned, is you varying the input, which is your delta noises on the denominator. And we want to see how it affects the output, which is the delta accuracy on your numerator. And that's what we are measuring. We could do this adaptively during the training time. And that's where we are moving. That can reduce the number of the augmented data that you need. Okay, so this sensitivity analysis for neural network, generally speaking, is not easy, but we have found that will be the way to go. And unfortunately, I'm not going to be able to go into all the detail on that, but this kind of give you some idea. That's kind of where we are moving. And so I want to sum up by just simply say that combination of this going forward to the future is the learning-based approach using simulated data does work. And it can make the system more robust. It addressed many of the technical challenges I mentioned and started with. And what we found was adaptive sensitivity analysis is one of the better way to go, because it actually increase the robustness, reduce the amount of augmented data you need. The other thing I do want to mention is we need to think a bit about model-based approach combined with a learning-based approach. And differentiable programming, differentiable physics, differentiable vision, differentiable geometry through backpropagation really can help accelerate learning in the physical world and certainly visual learning. We also have found using gradients in model-based RL, it was a tremendous help. And using active user feedback, like I mentioned, in getting the human feedback and learn the human behavior, it's definitely another direction that will be really helpful. Okay, I'm going to end right here. And I know I ran out of time.
Yeah, let's thank Professor Ming again for her great talk on a wide range of works on simulated data. Oh, yeah.
And then they're not listening, right? Nobody can hear anything.
Now they can hear.
They cannot because this is off, no?
No, that's broadcasting to the room. Yeah, but it goes to the laptops, the
see.
laptop sound still.
I wanted to mute because if I had this panel, then how will I unmute?
It's a way to hide it. Go to more. Yeah, if you go to more, I think. At the end.
Yeah, do you wanna do that?
And then hide loading meeting controls.
Hide.
Yeah.
Okay,
We can just keep it up.
all right, yeah.
And then start.
I can mute from here. Okay. So synthetic data is not the core of my research. We just used it lately as a way of improving generalization. And let me start by defining what I mean by generalization of visual representation. So during model training, we are given with a training set, a training data set, and we want to learn the parameters of a model by minimizing the loss with respect to some learning signal. That learning signal can be labels for supervised learning. It could be reconstruction for masked modeling, for example, or some form of matching pairs, either ground truth or created by transformations, right? After training, we want to be able to freeze the parameters of the model and use it as a feature extractor so that we can encode any image into a visual representation, right? And what we care about is for such visual representations to be as universal as possible. What does this mean? This means that apart from like all the training concepts and classes that we see during the training process that we described, we want the representations to be useful for other datasets that contain other classes, like datasets of fine-grained classification that are not the original ones, or the training classes seen in different domains, or even useful for other tasks beyond classification. And this is how I would define the generalization in the context of this talk as the model performance on unseen classes and test time distribution shifts. So now, in this talk, I want to talk about how we can leverage generative models. And I have generative AI there, but then I put it in quotations because it's such a hype term. So it's generative models, but these generative models are trained on billions on image text pairs, right? And they can produce high quality, realistic images given a textual prompt. For example, there's stable diffusion. You give it the textual prompt cat, and it outputs very beautiful cat images, right? Or there is a model like Instruct-Pix2Pix that you give it an image, you give it a textual prompt, and Instruct-Pix2Pix alters the input image, right, with respect to the prompt. Now, this talk is about how we can utilize such generative models for learning visual representations that generalize better to novel classes, to test time distribution shifts. And I'm going to present two ways of achieving this. In the first one, we're going to be using synthetic data, synthetic images exclusively for learning the representations, right? While in the second one is a more realistic case where we're using synthetic data together with the real data that we have for improving robustness to known test time distribution shifts. And there is relations and some common ground with the previous talk, by the way. We will be talking about very similar distribution shifts like snow and rain and at night with rain. Okay, but let's start from the first one. This work started when I was visiting Yorgos in Prague, and we're playing with stable diffusion that had just come out, right? And we saw that we can generate images of classes, and we're saying, okay, what is this? Do we still need real images for learning visual representations, right? So this first work is studying this. And to study this, we started with the most popular way of learning visual encoders, which is supervised learning on ImageNet, right? So in this very common setup, we have ImageNet. Everybody knows ImageNet, but let's repeat that it's 1,000 classes, right? 1.2 million images. So each one of those images has a label. We're minimizing a cross-entropy loss between its image and the correct label. Now, what we asked ourselves was, to what extent could we replace the ImageNet dataset entirely by synthetic images for learning the parameters of the encoder in the exact same way, right? So what we started from is just a set of labels, the 1,000 ImageNet class labels, no images. And we fed them to Stable Diffusion and synthesize images for every one of the ImageNet classes, the 1,000 classes. So Stable Diffusion takes as input a textual prompt and some random noise, right? So as you change the random noise, you can get many, many images for that same textual prompt. And that's what we did. For every class of ImageNet, you go and you see how many images are in that class, and we generated exactly the same number of images. And then we used these images in a data set that we named ImageNet SD, for obvious reasons, SD from Stable Diffusion, for training instead of the real ones. Okay, so as I said, the input to Stable Diffusion is a textual prompt, right? To generate images, we start from the simplest possible prompt that we could think of, which is the class name. Every class of ImageNet is associated with one or more synsets from a lexical database called WordNet. So if it's one, we feed that as the prompt. If it's more, we do a comma separated. We feed all the synsets comma separated. And we give that. And already we can see that even like this, we can have a data set, a clone of ImageNet from Stable Diffusion to train with. Now, the issue is that if we do this, there is a number of problems that arise. And this one is a nice one, because if you tell Stable Diffusion to generate images for papillon, Stable Diffusion defaults to generating butterflies, because French for butterfly is papillon, I think. I'm not 100% sure, I think so. The thing is that for ImageNet, papillon means something else. Papillon is also a dog whose ears are like butterflies, right? They're very cute dogs. But without any extra context, Stable Diffusion doesn't know that, and it generates butterflies. Okay, this is one type of errors that you can easily see. These are the easiest to spot, right? Then there is issues like domain. So for pirate and pirate ship, Stable Diffusion, and you cannot blame the model for that, it generates illustrations, right? However, ImageNet surprisingly has realistic images natural images of pirate ships somehow. Now, the third issue, and the most important one, was that we observed a generic lack of diversity. If we just do this, you can see it even from these few images, that there's very little variability. We get images where the object fills the whole image, is kind of iconic. And I have an example here. I'm so sorry. Where on the one side is ImageNet images, real images for the class lorikeet, that parrot. And here is the Stable Diffusion images for the same class. It's obvious that the diversity is far worse for the Stable Diffusion case. So we tried to fix that. And to fix that, we said that, okay, we need to provide Stable Diffusion with kind of more context. And we wanted to do this in a as generic way as we could. So what we added as context is the hypernym and the description of those synsets from WordNet. WordNet is some sort of graph tree ontology. So for every class, you can get kind of the parent class, right? I'm sorry. So for the dog, the papillon, the parent class is toy dog. So as soon as you append that to the prompt, you immediately get the correct images. Correct, the right images. It also helped a little with domain issues. For example, pirate ship, because the description is talking about something like a ship of pirates, I don't remember, but it's more descriptive, right? So it made Stable Diffusion to shift away from simply doing illustrations. Then to fix diversity, the first thing we tried was something very hacky and complex, and it's this, where we said, okay, almost all the images we generate have the same background. What if we would diversify the backgrounds? We said, okay, let's find very generic background scenes and add them in the prompt. So you want a lorikeet inside a bookstore. So we took all the classes from places and we generated images like that. And this kind of worked, but not really. So from afar, and I hate that I cannot see the screen, by the way, I like to look at the screen. From afar, it looks maybe that all these images have parrots, but there is many that don't have parrots. There is, let's see, this is a ball pit. Over there is some sort of grocery store, like the farmer's part of the grocery store. Up there, there's some convenience store where the leaves of that plant are like parrots. There's many. It's hard to spot from afar because Stable Diffusion does a great job of hiding it. There's so this one is like a gallery where the vases have the colors of those parrots. It was very interesting to visually inspect all that in many classes. It was fun. But what we see is that we increased the diversity, but in many cases, we lost the class that we cared about. So what we then thought of is, okay, can we tune Stable Diffusion to give us images with more diversity? And for that, we went and we changed this parameter called guidance scale, which is how much do I depend on the textual prompt for generating images, that is, let's say, I think it's between 7 and 8 for the stable diffusion that was out there back then. This was stable diffusion 1.4. This is 1 year, at least, old work. We tuned it down to 2 or 3. And what we saw is that, okay, we lost a decent amount of fidelity in the images, but we gained a lot of diversity. I think, yeah, I have an example here for the same class, always the lorikeet class. We see now that, first of all, there are multiple lorikeets generated in many cases. The diversity of the backgrounds exists. Overall, we have images that are far more diverse, albeit if you look closely, if you would see these images in a larger, you will see that they miss fidelity. So we sacrifice fidelity for diversity. Okay. All right. We didn't want to go deep with prompt tuning and prompt engineering, so we stayed there. And we synthesized for each one of those prompts different clones of ImageNet. And we did this for 2 cases, the ImageNet 100, which was smaller, and we could, in terms of compute, it was easy to generate fast and try a lot of things. And then we tested things at the larger ImageNet, the popular ImageNet 1K dataset, right? Unless I say something else, we always create the same number of images as the original dataset, right? We study the 1-to-1 case. The training and evaluation protocol is very simple. For training, we use only synthetic data, right? We use ImageNet SD to learn the encoder and the classifiers. And then at test time, we freeze the encoder and the classifiers to measure performance on ImageNet. Or for transfer learning, what we normally do is we learn linear probes, we learn classifiers for the new sets of classes for each one of the downstream datasets. This is what we did here too. But the encoder parameters are all frozen. So they're learned from synthetic images. We always test on real images. Okay, and here is how the prompts that I just described perform on the ImageNet 100 dataset. We see that you can do a decent job of 43 accuracy out of 100 classes if you just put the class, but then solving all the issues that I mentioned increase performance, which the thing that made the biggest gains was, I'm sorry, reducing the guidance scale of stable diffusion. Okay, and this looks fine. And we see that as we address the semantic and domain and diversity issues, we get better performance. However, compared to how much you could get by training on the real ImageNet 100, there's still a significant gap. So then we thought, okay, a big advantage of using synthetic data is that we're not limited by how many we can generate. So let's start generating more. So we started generating more, and we saw some gains. And we saw that at 10x, we can get decent gains. And we said, okay, that's great. Soon we will reach the performance, but that was not the case. So we increased and we went up to 50x the size of ImageNet 100, but we saw no visible gains after a while. And it seems unlikely to ever close this gap, right? And this is for the training classes. Okay. But what we were mostly interested in general, our research is about generalization, right? So we started measuring performance on many other transfer datasets. And there, even from the beginning, even in the 1-to-1 case, we see that we have 56 with 58. It's pretty close, the performance that you can get with a model trained with 100K synthetic images versus 100K real images. It's, very small gap. But then as we started generating more and more images, we saw that we saw pretty decent gains of up to 5% accuracy over many datasets. This is over 10 datasets of, fine-grained classification, long-tail datasets, concept generalization datasets. So the representations from the model that is trained on synthetic images outperform the ones from real images, okay? And we studied this in a small scale. There is a paper at CVPR now that studies it at a much larger scale with a lot more compute and resources. And it's a nice paper, you should read it. Yes, so let's look at what happens when we go to a much harder task. This was 100 classes. Now we're talking about classifying 1,000 classes. ImageNet 1K. It's more or less the same situation, right? We have almost half the performance of the best possible model, RSB. I forgot to say that all this is with the ResNet 50. And then what we see is that as we look at data sets of the ImageNet classes in other domains, the gap reduces, but it still remains the same. Now, what I need to say here is that our classifiers are still trained with synthetic data. If we would train a linear probe, oh, I think the mic is out. It's happening. Okay. If we train a linear probe, we can go all the way to 70, but still there is a gap, right? There is always a gap for the training data. When we look at transfer learning, compared to the best possible supervised model, the RSB model, we see that we can beat it with 1x. This is one-to-one comparison with 1.2 million synthetic images. We can have a model that, transfers better to 15 datasets, including iNaturalist, very hard datasets. And we hypothesize that synthesizing more images could help improve the gain, and it seems to do. So let me summarize what we talked about so far. What if we replace the ImageNet dataset with synthetic data for stable diffusion? Well, we can still train models from scratch using only synthetic images, and we can get decent performance on the training task, but not as good. But when it comes to transfer learning and new classes, we learn a model that generalizes better. Okay, and this was shown in many cases. I have this teaser slide that I made a couple of hours ago. That is some newer results that we have, where we use this dataset, this exact same ImageNet 1KSD, for distillation. So in this setup, we have strong models that are good at different things. Like, for example, Dino is good at generalization. iBot is very strong at dense prediction. Like, so if you get a linear probe for segmentation and depth, iBot is very, very strong. You have Date3 and DBot that are very, very strong in ImageNet. And we take all these as teachers and we distill them using ImageNet SD. And we see that for all the transfer learning tasks, we can improve with synthetic images. So this is not out yet, it's going to be out soon, but I wanted to say this. I'm very excited about this work. Okay, so this was the first part of the talk. Should I stop for questions now or in the end? How am I doing on time? Okay, all right, let's do it at the end. I apologize for my throat. It's like every time it happens, so I don't know what to say. It's stress. Okay, let's go to the second way of using synthetic data, and this is something more realistic. Okay, there was a great study. We can only use synthetic data for training models, but now we have real data and we want to use them. What if we have known test time distribution shifts? Can we use these generative models to simulating those shifts? And for that, I will shift to a task that is fit for this. And this is the task of long-term visual localization, where the idea is that I have a database of images with known 3D poses, and then I want to estimate the pose of the query, a new image, given these poses, right? I want to output the 3D pose for the query. How do you normally solve this task? You solve it in two steps. First, you need some sort of fast way to get candidates, the top candidates from your database, because the database can be, 2 million images, can be a whole city. You do first some sort of fast retrieval with global features to get the top candidates, and then you give these top candidates to some amazing matching technique, for example, Duster or Master, to advertise my colleagues' work. To do a more precise pose estimation, right? This task has a set of challenges that are known, right? These are extreme appearance variations that could be caused by weather, seasonal, or time of day changes. Here is a figure from Torster's paper where you see the same exact location in 4 different times of day. And you see how different the visual appearance of that place is. You can imagine that with a global descriptor, it's going to be really hard to capture this. That's why we said, can we use generative AI models to synthesize such domain shifts? And we do that because all of these concepts, all of these domain shifts I presented can be very nicely explained in language. Okay. So our goal is to improve the retrieval step. We care about representation learning, right? We let Jerome do the matching and do amazing post-approximation. What we care is to give them the best possible shortlist to test with their methods that are far more computationally expensive, right? So we want to improve the robustness of the retrieval step, because if you miss a very good image at the retrieval, you cannot do good post-approximation, right? So for this study that I'm going to show you, we're dealing with basically image retrieval. And the post-estimation part remains fixed for all the methods. And yeah, the role of retrieval, as I said, it's very, very important. But what normally people do in visual localization is that they take the best place recognition or landmark retrieval method, and they don't optimize it for the task. So what we did is we went and we optimized it for the task. That is the first thing we did. I want to go fast because it's not really related to synthetic data. So we started from a model that is state-of-the-art. We found, and studies found that it's state-of-the-art for landmark retrieval. And this is the model, a model called How. This model is training using tuples. Tuples means that I have two positive images, query and positive. These are two images of the same location, right? And then I have some negatives that are hard negatives. You can mine them at every epoch. The way you're learning representations in this How model is with a contrastive loss and max margin loss. You bring the query close to the positive, right, and far away from the negatives. So what we did is we tuned this and hyperparameter tuned this for localization accuracy, right? And this resulted, what we found worked most is like very strong data augmentation and things like randomly sized crop that were missing from How, and we changed with the optimizers and schedules and training. So this is to make the core training better, right? Now, then what we did is that we used generative models to synthesize images for the domain shifts that we cared about. I already presented in Struct Pix to Pix. In Struct Pix to Pix, get an image and a text, and it changes the image with the text. This is what we did. We took every training image, and we created textual prompts using the most common domain shifts that the task has, which is exactly the prompts that you see here. There's no much more prompt tuning. In summer with rain, at night with rain, at night, in winter, right? So you give Struct Pix to Pix the original image and this prompt, and you get results like this. This is the Acropolis. We see the Acropolis with snow, which is not very, very common. Okay, so this was it. Now we have a data set that is 11 times larger, right? So how do we utilize these synthetic images during training? We utilize them by forming synthetic tuples where one of the two images of the positive pair is replaced with a synthetic image together with all the negatives. Why do we do that? We replace one of the two images of the positive pair because we want to match the original image, one of the original images of the pair, with the at night image of the other, right? So we want robustness across domains. At the same time, we want the at night image that we have replaced in the tuple to be far away from negatives that have the same transformation, right? Otherwise, the negatives would be too simple, too easy to distinguish. So we create such synthetic tuples where the positive is one real, one synthetic, and then the negatives are synthetic. And for every real tuple in the training set, we sample k synthetic ones, right? How we sample k, I will discuss still more. And the loss is computed very simple. We average over all the original tuple and the k synthetic tuples. All right. So if we do this generation process, this is an automatic generation process, huh? And sometimes it works really good. If you see on the left, for at night with rain, it puts reflections down in Struct Pix to Pix out of the box with some command line level hyperparameter tuning. It worked really, really well for the domain shifts that we cared about for visual localization. But in other cases, like the one on the right, the output image is losing any location characteristic. And what we're doing here is we want the two images of the positive pair to show the exact same location, right? We want as much as possible to preserve such location characteristics with quotation because what that is unclear. So we thought, how can we devise a way of automatically figuring out that case that the image is destroyed after we synthesize? And to do that, we went to task priors. So first of all, we're training with matching pairs, right? That's a very good thing we can use because we synthesize one image, but we always create a pair with a real and a synthetic image. And two, we know that geometry is important for preserving locations, right? So this is what we did. We made this very simple hypothesis, which is that the geometric consistency of a matching pair should not change significantly when one of the images is replaced by synthetic variant. So we see here 2 images of Montjuic in Barcelona, right? And then we replace at the second row, we replace the first image with the at night with rain. Okay. And what we saw in green there or yellow below are the correspondences that are found with out-of-the-box matter, right? This is light blue. We used light blue back then. Master wasn't out. We used light blue. What we see is that we replace the image, the first image, and a lot of these correspondences do remain, right? In the second case, where the location characteristics are completely destroyed, we see that a very small percentage of those remain. So this is what we said. We defined the geometric consistency score as the ratio of the correspondences remaining after replacing the image. And then how do we use that? We use that in 2 ways. One, if the correspondences drop a lot, we remove this synthetic pair. As simple as that. Is a bad pair. 2, for the images that pass this threshold, we want to sample the hardest possible cases, right? At night with rain, of course, keeps far less correspondences than if you say in summer, right? Which alters the image little. So we used the inverse of this geometric consistency score to sample tuples, right? We said we sampled k synthetic tuples for every real tuple. This k is like 3 in practice. Which 3 should I select? Well, you select randomly with inverse probability of this. Let me refer to this figure down there, where it shows that, of course, after this geometric process, the different prompts are not dropped equally. Some are dropped more than others, and the one that was dropped significantly more than others was a sunset that has a very strong visual characteristic that destroyed a lot of things. Okay, I don't think I have a lot of time. I'm not going to stay a lot with results. I'm just going to show you the summary, right? We tested this on 5 localization datasets. Here we split it also day and night to show how much better we do for the night. No, it's common to split robot cars and Aachen with day and night, but it's 5, the most common localization datasets, right? And the black dot in the middle is the state of the art at its dataset separately. And what we saw is that first, with the modifications we made for the training, we get a lot of gains. And second, we get extra gains by adding the synthetic data and the geometric constraints. What was surprising is that in the end, we saw gains in datasets like Gangnam. Gangnam is a dataset for indoor localization. And we saw gains, although our prompts are clearly made for outdoor and weather, we also saw that it had a regularization effect also for indoor datasets. The other thing that we did is test this out of the box for all the common place recognition datasets, and it worked out of the box with state-of-the-art results. It worked very well. So going back to visual localization, we measured visual localization in 2 ways. The top one is a fast protocol where you get the shortlist that I said, and you just average their poses. And this is a protocol where retrieval, what we change, matters a lot, right? And over there, you see we have gains of up to 14% in some cases. Now, we also wanted to see if we keep some of those gains after we replace the second part with some sort of very strong state-of-the-art poses approximation, right? You can imagine that a good pose approximator on the top 50 would do a better job, right, than the average pose. And we see that we still have gains on top of, for that case too, where a 3D structural motion map is used and you register your query in the 3D map. Okay, let's summarize this work. We showed that visual localization is a very good candidate task to use generative models for. And I'm like, I should have spent more time adding related work slides. This, like, I think half of the talks of today are saying the same thing, right? Like we're using synthetic data as a data augmentation. So if your generative model models part of the distribution there, you can use them as data augmentation. Why we can use generative models? Because our domain shifts can be expressed in plain text at night, you know? And what is more interesting maybe here for this work is that we went back to the task and we found a way of automatically validating the synthetic data, right? How did we do that? Using geometric consistency. Yes, all right. So just to summarize this talk overall, I presented you two ways of utilizing generative models. I have generative AI and generative models, very inconsistent. Generative AI is not a great term. For improving generalization. Okay, these are the two works. If we take one step back and see what I was talking about, what I think we're doing here is the following. The first one, where we're taking images from Stable Diffusion to train a model from scratch, we're kind of doing image-free distillation of this, of the knowledge that generative AI model has for the classes we give it into a purely visual encoder. And then in this way, we can have an encoder of arbitrary size, right? An arbitrary architecture. In the second case, we utilize the domain-specific knowledge of a generative model as data augmentation with automatic validation using task priors. And I have to finish with a caution tale with generative data. You have no idea how easy it is to generate bad content with these models, even these ones that I refer to. Even if you play with the ImageNet 100 categories, you see problematic cases. Okay, we have to always remember that generative model data inherit and amplify the biases that are present in the generative models training data that maybe are not even, it's huge and hard to, really hard to even inspect, right? Verification becomes crucial. And in general, beyond CVPR and closed benchmarks, generative AI data should be used with extreme caution. And I don't remember what was the prompt for this New Yorker style cartoon there, but this is what the model generated about this slide. I gave it the text of the slide and I told it to generate an image and a caption in the style of the New Yorker for this. It's it's ChatGPT-4V, but yeah. Yes, this is it more or less. This is research with amazing co-authors. Bulend and Diane are in both of these papers. The first one is with Kartik, the second with Philippe and Rafa and Gabriela. And just to advertise our little bit more generic work, I'm sorry, this is a small part of our core research, which is around generalization in different ways. And I'm by far not an expert on synthetic data. You saw we used the big models that are out there as black box, right? We did not much in terms of synthetic data. But this is part of a quest, let's say, for concept generalization that we're doing that starts from like how we can measure concept generalization better, or how we can use the tricks of self-supervised learning to improve supervised learning, or how we can have complementary models with different generalization power. Can we retain it and put it all in one? Or can we improve generalization at test time, you know, with test time training or label propagation? Or should we have more expressive representations to do better representation, better generalization? And before I finish, I have no paper on synthetic data in this conference, but we have this paper, and it's a nice paper with Yorgos and Vladan. It's about zero-shot classification. And we're using essentially label propagation on a graph of unlabeled images to improve it. It's great. Come to our poster. And that's it. Thank you. These are renderings of images that I took of the Navar offices. The Navar offices are beautiful. They're kind of like this. So here it is. Oh, no, yeah, I expected this laugh. So look, here is the original images. They're very close. I'm going to go back and forth. You see. This is really this is where our work is. It's beautiful. This is a chateau in France. Anyway, thank you. I did 38.
All right, thanks so much. So I think we have time for one or two questions. Anybody?
Yes, please.
Hi, thank you. I have a question about, so for the first part of your talk, you talked about, pre-training with these, teacher models by
Ah.
distillation.
Yeah.
Did you at all consider, using the latent space of the diffusion model itself and distilling that into your child network, or?
This is a very good question. We tried some preliminary experiments. The thing is that for that work, I'm sorry, this is like, yeah, it's a teaser. It will be out soon. For that work, it's again a study, right? We want to understand the distillation part. So we fixed the training data to ImageNet. All teachers are, so it's iBot and Dino and Date3, they're all trained on ImageNet 1K. So this excluded models like Dino V2 and Clip and Stable Diffusion that we tried afterwards. It's in the paper, but yeah, in the main study, we didn't try it. And trying ImageNet SD is something we tried very recently as a way of, we have this data set. Why don't we also use it for distillation? It seems good for transfer learning, and it proved good also for distillation. Thank you.
We have time for one more question. There's others.
Oh, sure. No, yeah, why not? Advertisement.
Thanks for the presentation. It's very impressive, and I'm also curious about like in your first topic. So you use the like augmentations for like change like in the InfinGen, and I'm curious about like because usually like generative models also has their knowledge agents, or like how to say it, like when you training on large data set, there will be like more dogs than the. So there will be more dogs than like the tigers or like other animals.
Mm-hmm.
So when you generate the like generating the training set for the models, and it could be more failures in like generating tigers than dogs.
Of course. Yeah, very good question. So the only reason this works is because our generative models can represent well the part of the part of the space where these class names are. And why? Because these are very popular names. If we're out of that distribution, it's going to generate crap. Same with at night, and in the second case, right? It's very generic things. Of course, it knows about how something looks at night and with snow. It's a relatively easy way to infer when you're trained on 1 billion images, text pairs, right? So you're very right. If it's obscure classes, it wouldn't work at all. We tried a number of things. There was a great talk yesterday at a retrospective workshop. But this professor at Stanford, I forgot his name, that was touching this subject, he presented in a very nice way, right? Each one of those models is good at specific places where the training data come from. Outside of there, even if we keep on adding and adding and adding data, we will never cover the whole visual world. So in all the in-between places, you cannot generate. That's it.
Thank you.
The question becomes, does it matter if we cannot generate very obscure things, right? Is always, why do we want to use this for? So usually for what we need to use it. For example, the second paper is a real use case, right? This is a model for localization that can be put in an autonomous vehicle. Over there, it worked. Yeah.
Thank you.
Thank you.
All right, so thanks again.
Thank you so much for the invite.
Welcome to the synthetic data for computer vision workshop. My name is Jiao Zhang. I'm a fourth-year PhD student at the University of Washington. My research is primarily focused on data-centric AI, where the synthetic data is a big part of it. And I will be on the academic job market for the 25-26 cycle. Feel free to reach out if you're also interested in data-centric AI and want to discuss it. So first of all, let me briefly introduce our organizer team. Chenyu, Zixian, Weikai, and sorry, Ranjay and me are all from the University of Washington. Shobita, Philip are from MIT, and Weijo is from Cornell. We are all very excited about the future of synthetic data for computer vision. We also have a wonderful lineup of speakers from both academia and the industry. They're going to cover a wide range of recent advancement in synthetic data for computer vision. In addition, our workshop has more than 40 posters, and the post session will be from 1:30 p.m. to 2:30 p.m. And we also have 2 oral presentations from the accepted submissions. We will announce paper award at the closing remarks. So, why do we care about synthetic data, particularly in the context of computer vision? Because there's a long history of synthetic data for computer vision, and these applications has driven many advancements of many fields in computer vision. For example, the open-rate synthetic simulation environment for robotics, and the color for autonomous driving. And for image understanding, we have both Clever and GQA. They synthesize question and answers to form VQA benchmarks, and they have driven the early developments of VQA system. So what do we have now? Now we have many new and better synthetic simulation environment. For example, we have behavior, Unison, DataComp, Procedural, and many others. And recently, we have many new ways of leveraging synthetic data for computer vision. For example, we can use synthesized novel views for better robot planning. And we can learn better visual similarity with synthetic data. We can also improve our multimodal data set with model-generated synthetic captions. We can have better image editing model using synthetic training data generated from synthetic 3D scene or environments. And finally, I would like to share our recent work from the University of Washington. It is titled Ask Me Anything. It's a which can generate benchmarks tailored for users' need for assessing multimodal language models. So as a benchmark generation system, it contains more than 300 object categories, more than 600 attributes, and more than 300 relationships. It has 28 task generators. They are just Python programs. And all these concepts and the task generated together, they can possibly generate over 700 million image QA or video QA tasks. And all these are just programmatic generation, no models here. So the right figure is a comparison of the task space between Task Me Anything and all the existing static VQA benchmarks. While Task Me Anything can generate a huge amount of VQA tasks, we only maintain the 28 task generators like Python codes and the necessary visual assets and the knowledge base in our disk. So the task can be generated in an on-demand manner. And it is also very easy to expand the task space of Task Me Anything. One can add new concepts or new task generators to exponentially increase the task space to support more and more user queries regarding model performance. And also in this work, we support fine-grained user queries. For example, here, we can ask the top 5 objects that GPT-4o is worth at recognizing when rotating. And to avoid evaluating a model on millions of tasks, we also support on-budget query result approximation so that we can get these top K results within a given budget. And here is an overview of the Task Me Anything system. So basically, when a user comes with a specific query, they can use our system to identify, generate, and evaluate their model on relevant tasks to get the idea of the model performance. Okay, that's the end of opening remarks. Thank you again for attending our workshop, and please enjoy the wonderful lab of talks and posters. And so yeah, so our first speaker is on the way. So let's our first Professor Ludwig Schmidt from University of Washington in AI.
So I didn't see it. Oh, it's not. It's active walking late. Okay, so oopsies. I should also join the Zoom link.
Yeah. We have a link. Yeah. Okay.
Okay, now we are good. Okay, excellent. Next step. Okay, as I said, now with some delay, we'll start with a journey through 2 years of data sets for multimodal learning. And specifically, to get us all on the same page, what do I mean by multimodal learning? This thing is still not working, and I think I know why. Okay, to focus back on the window. Okay, excellent. And just to set the stage, when I talk about multimodal learning for today, this is going to be 2 topics. The first one is image understanding, specifically in the form of image classification, like good old ImageNet and so on. And the second one is generating images. Basically, one is image in and you produce the label. The other one is text in and you produce the image. Okay, these are obviously very widely used or very widely studied problems. So the models that come out of this are very widely used. And one important sort of like milestone in this entire multimodal learning research direction was early 2021, when OpenAI released the CLIP and DALI model. Right, I'm sure everyone here is familiar with these two. CLIP is a model for zero-shot image classification, among many other things. And DALI is a model for image generation. Since then, there's been lots of progress, but these were really 2 milestones. And one aspect, one reason I particularly cared about CLIP was that it does really well in out-of-distribution robustness, many other cool reasons for liking CLIP. And then DALI obviously set the stage for this entire revolution in text-guided image generation. Okay, and the common foundation for both of these advances was a very large training set that people at OpenAI had built. Specifically, for CLIP, this was 400 million image text pairs. I'm not sure if they put it in the paper exactly how much they used for DALI, but in general, this training set was just much larger than what people had in open source AI and public research at the time. So Google probably had similarly large data sets, but for us in open source, this was a big challenge. So, and then what we did over the past couple of years was basically take steps towards building large and high quality data sets for multimodal learning. And this is what I want to talk about today. First, the Lion 5B project, which was the first billion-scale image text data set. And then the follow-up paper, DataComp, where we sort of used Lion as a starting point, and then studied how can we make these image text data sets even better. Cool. So let's get started with the first one, the Lion 5B paper. This was a large collaboration with many people. One thing I like a lot about open source AI is it's sort of like very grassroots driven. You have people joining from everywhere. And as the name suggests, the whole point here was to build a data set with about 5 billion image text pairs. So specifically, the breakdown is 2.3 billion English, 2.3 billion multilingual, and then 1.3 billion that were not really language specific. So you can think of an image of Paris, and then the caption is Paris. Is this sort of like French or German or English? So this is in the third bucket. And yeah, as I said, many different people involved, big community effort. And so the important point here was that even if you just look at the English subset of Lion, this was more than an order of magnitude larger than the prior state-of-the-art and public image text data. Before that, the largest one that people had put out was the YFCC dataset with 100 million image text pairs. And then at the same time, with Google and OpenAI, you already multiple 100 million or billion. This 100 billion number for YFCC, this is also before filtering. If you actually filter YFCC for doing CLIP-style training, you are left more with like 20 million images. Okay, cool. So how did we actually build? Like basically all AI progress over the past 10 years at some level, it's based on the internet and specifically Common Crawl. So the starting point for this data pipeline here is Common Crawl. It's a very important open source project and they crawl the internet. And specifically, what we got out of Common Crawl was a candidate set of 50 billion image text pairs. So these are just image tags in the HTML together with the associated alt text, right? If you remember HTML coding, image tags, of course. And then you can also always put an alt text into these image tags in case the browser can't display the image, they'll display the alt text instead. And overall, this is pretty noisy. Like if you look at HTML source, alt text is a pretty noisy way to get image annotations. But the good news is we have 50 billion of them. So we can do a lot of filtering to keep only the good parts. So this is what we basically did. We built then a filtering pipeline that starts with Common Crawl. and then does some basic web page filtering, and we downloaded the data. The most important part of the pipeline is really this one here. So we have all of these image text pairs. Overall, it's quite noisy. How do we build a high quality subset out of it? And the key idea here was, let's use one of the existing flip models from OpenAI because they were already out there, and use this as a quality filter. So what we did was take an image, feed it through the image encoder, take the corresponding alt text, feed it through the text encoder, and then you can look at the cosine similarity between the image and text events. And if the cosine similarity is above a certain threshold, we say this is a good image text pair, let's keep it. If it's below a certain threshold, then we discard it. Okay, this was a bit ad hoc, but at least based on visually inspecting the data, it looked like a reasonable start. Okay, and then there are always questions of like how good is this data set actually? This is different from what they did at OpenAI. They actually built it from scratch. They didn't have the club model sets to filter. How does our training set compare to what they had at OpenAI? So in order to judge the quality of the training set here, what we did was take our data and then train clip models on it, because overall, one way of measuring data quality for AI is how good is the resulting model. And when you do this for small scale clip models, B32, then this was a very nice outcome. Actually very good. Maybe like 0.5 percentage point worse on ImageNet or ObjectNet, but definitely the right ballpark. And this data set then had a lot of impact. It's widely used, got a best paper award, and has become the training set for many state-of-the-art models. One obvious one being stable diffusion. I mentioned this earlier. Image generation is like one of the main consumers of these image text data sets. They build on Lion. And then the other thing, this is out of my group, we built OpenClip, which has become sort of like the most widely used repository for training open source clip models. And some of the state-of-the-art clip models you can find in OpenClip. So especially Gabriel and Mitchell's work. Now they've graduated sadly, but they were also PhD students. Cool. Okay. So far, so good. This looks like a really nice data set. But there was sort of like a catch, which we realized as we scaled up the models. And this was that as we made the model, the clip models we trained larger, the gap to the OpenAI reference numbers kept going up. So specifically here, if we now train an L14 model instead, then the gap to the OpenAI trained clip models on ImageNet grew to 3 percentage points. And then on ObjectNet, it became 9 percentage points. And this was really a bummer for me, because personally, sort of like from my research background, one reason why I really cared about the clip models was that they had a lot of out-of-distribution robustness. But now we're actually losing quite a bit of it. We have a 9 percentage point drop compared to the OpenAI number on ObjectNet. So what should we do? So like the question was, how can we build sort of like better versions of Lion, better multimodal data sets? And this is exactly what we then set out with the DataComp benchmark. It's on a high level. Why do we want a benchmark for data? So for me, when I think about AI, it's really two components, the compute and the data. And the left-hand side is what I think still most of the papers are about, right? There are a lot of papers about optimization algorithms, different model architectures, loss functions, and so on. I think this is great. As a community, over the past 10, 20 years, we have learned a lot about how to build good models. I think what we have learned less about so far is how to build good data sets. So when we were stuck with our Lion data set, it's sort of like 10 percentage points worse, roughly, than the OpenAI one and ObjectNet. So like, what do you do? How do you close this gap? I think one thing that's really cool about like the workshop like this today, or like that NeurIPS now has the data sets and benchmark trackers, that we're starting to learn a lot about the data side of machine learning as well. And specifically one thing that's worth keeping in mind is when we have sort of like this nice progress on all of our benchmarks, this is a very rigorous process, like controlled experiments. Everyone uses the same data. So we learn a lot about how to compare different training algorithms and model architectures, but we learn less about how to build a good training data set, because everyone uses the same training data, right? This is both good and bad. It's great because it's a rigorous, fair comparison. The downside is if we never change the training data, we learn less about how to build good training data. So the idea with DataComp was, let's basically flip this around and build a benchmark for multimodal training sets. Okay. So like what we basically did here was, let's start from Lion, but rebuild it from scratch. So Lion was basically a one-time effort. the data pipeline that we used for Lion only really existed at different stages at different points in time. It's not something you could easily rewrite. Okay, if we want to make it easier for people to experiment with dataset construction, we need to build a sort of like toolkit that allows you to build Lion-like datasets from scratch. And then you can do a lot of ablation experiments and so on to figure out which of the parts really matter, how can we make a dataset better. And then once we have this tooling in place, let's also set it up as a benchmark so we can have sort of people participate and see who does best. And so like, as I mentioned, this is the idea here is let's flip this traditional ML benchmarking paradigm around. Normally, we have data sets fixed, and then we improve the model. Now we fix the model training code, and we have people improve the data set. Okay, so this is all nice at a high level. What does this actually look like concretely? What do we provide as part of DataComp? So like the core starting point for participants is our large image text candidate pool. So we have 4 different scales in DataComp, going from 12.8 million to 12.8 billion, so a factor of 1,000 in the dataset size. And this pool is basically from Common Crawl with minimal filter. We did a little bit of filtering for you so that the toxic content is removed, and we do some face blurring to make sure people's privacy is protected. But overall, the idea is, apart from the safety interventions, is as unfiltered as possible, so that when you participate, you can experiment with all sorts of different filtering methods. And we give you standardized clip training code and an evaluation test bed of 38 downstream tasks. And then your role as a participant is twofold. You can either participate in a filtering track, which means you use only the data that we provide from Common Crawl and build a really good subset for training clip models, or you take part in what we call the bring your own data track. If you're like, okay, I have this extra super nice data, maybe it's synthetic data, maybe you have like a super nice synthetic data generation pipeline, and you think this is great for training clip models, then you can also enter this competition, but we put it into bring your own data track because you have more flexibility than just filtering. Okay, cool. This is all nice, sort of like in theory. How sort of like interesting is this design space? Can you actually make progress on multimodal training sets in this DataComp framework? And we were curious about this ourselves because we put a lot of effort into building this benchmark. And the answer is yes. So this is the table I have shown you earlier, where we have OpenAI, Lion, and we had a gap between Lion and OpenAI for training large models, L14. And now the very nice outcome here was when you train a L14 size clip model on DataComp, you actually do better than the training set. Here, this is a 4 percentage point improvement roughly on ImageNet and a 5 percentage point improvement on OpenAI. So I was super happy with this. And so like for us, this was just a start, because we wanted to show that within this DataComp framework as a baseline, we can actually substantially improve over Lion and OpenAI. And to the best of our knowledge, this was the first public training set that improved over those. And this has already become sort of like commonplace in various large tech companies as a starting point for their own data sets. And another way of thinking about this improvement is a 9x improvement in compute efficiency. So previously, when we only had Lion, we were interested how far can we push the model. And we could actually train a model to 79% on Lion as well. It was just a much larger clip model trained with a lot more compute. And now we could get to the same 79% using 9x less compute overall, which is a substantial saving. Just for me, quickly for context, how much time do we have overall? 20 minutes left. Okay, plenty of time. This is great. Cool. So let me tell you a little bit about what went into this DataComp 1B training set. Like, how did we get these improvements over state of the art? And because we already knew how to build Lion, we thought, okay, let's start there and see if there's sort of like low-hanging fruit in the Lion dataset creation pipeline, where we can just tweak a few things better and get some nice improvements. And sort of like the most important thing here is the similarity threshold, right? I mentioned earlier, when you build Lion, the key step is using a clip model to filter the image text pairs. So you compute the cosine similarity between image and text embedding. And now the question is like, what counts as a good data point? So like one thing we looked at is, okay, as we vary this threshold, how does the accuracy of the resulting models behave? So this is what you have here. X-axis is fraction of the tool that you keep. Y-axis is performance, either just on ImageNet or on an average over all of these 38 tasks in our benchmark suite. And then you can see, okay, peak is around 0.2 or 0.3 fraction of the tool. Like previously in Lion, we were actually a bit too conservative in the too stringent threshold. So by relaxing that, we were able to train better models. The next thing we did was remove the language filtering. So we thought, okay, in Lion, we should probably do some language filtering and separate it by language, as I mentioned initially. But it turns out language filtering in itself is sort of like a noisy process. Sometimes the language filter is incorrect. So for the DataComp B dataset, we just took out the language filter and we let the CLIP model decide itself whether it understands a data point or not, right? And in the end, it has a text encoder, and we can just look at CLIP score and then leave out the explicit language filtering step. Cool. And then the third ingredient here was image clustering. This was just a bit of a hack that we came up with towards the end. We were curious, okay, what happens if we rebalance our data a little bit? So we did some clustering of the data set, starting from the ImageNet images, and then we filtered out image content if it's far from these clusters. The state-of-the-art data sets don't use this anymore, the CLIP filtering. I think this is worth remembering. The other two parts here, I think, are in retrospect less clear if they actually how much they actually helped. Cool. Okay, so this is how we built this new data set. There's one other point in this DataComp benchmark that I'd like to highlight, and this is sort of like how the performance at different scales relate, right? So if you think about training large CLIP models, this can cost sort of like tens of thousands of GPU hours. So I think an L14 CLIP model is 40,000 A100. So this is obviously very expensive, and you can't just try random ideas at that scale. So one thing that we paid attention to with this competition design and DataComp was how can we make sure these smaller tracks in the DataComp benchmark actually give us predictable signal for what works at larger scale, right? And so specifically, as I mentioned earlier, we have sort of like these 4 different scales. 3 smaller ones are here, 12.8 million, 128 million, and 1.28 billion pool size. And then the question was, okay, if I have a data curation method, can I try it out on the small and the medium pool sizes? Is the performance actually well correlated? So this is what we did here. X-axis, ImageNet accuracy of a filtering method evaluated on the small scale, and then Y-axis is medium scale. And overall, you see that we have a pretty good correlation. It's not perfect. There are some points a little bit away from this trend line, but overall, this is a pretty good trend. And this also holds for going from medium scale to large scale. Again, not perfect, but overall, a pretty good trend here. And so what this enabled us to do was most of our experiments at the small and medium scale, see what worked well at those scales, filter out all the bad ideas, scale up the remaining good ideas, see what worked best at the next large scale, again, filter out the things that didn't work. And then in the end, we had sort of like, I think 1 to 200 experiments that we ran at medium scale and only 10 that we ran at the end at the very large scale. Cool. Okay. So this is sort of like what we did in this DataComp framework. One thing that was cool to see is that after us, all the different researchers picked this up. In short, there's still many different avenues for improvement. This is one very nice paper from CMU, from Seco and Aditi's group, and they looked at specifically images with text in it. It turns out when you do this CLIP filtering, CLIP really likes reading text and images. So some of the image text pairs with the highest CLIP score are those images where you have actually text in the image and then the caption is the same text. And whether this is good for training an image recognition model or not is a little bit unclear. So what they did in this TMARS paper was, so first of all, exactly measure the effect of the image text pairs with explicit text in them, and then come up with creative ways of masking out the text so that you can overall get gains on the image classification benchmark. So overall, at medium scale and DataComp, we saw a 6.5 percentage point increase. people also just took this data set here and trained some new state-of-the-art club models. This is from Sihong's group at UC Santa Cruz. They trained a state-of-the-art club model, Club A, by taking their modeling improvements and then training on DataComp instead of Lion. And then finally, since I promised some results on synthetic data, this is a nice paper Thao, one of my students, wrote, which is about improving multimodal data sets with synthetic captions. Thao is I think she's in the workshop today. I haven't spotted her yet, but if she's around, she's the expert on this. And I'll just give you a quick overview. The idea here was as follows. When you just look at the raw data in this DataComp pool, you see that there's a lot of image text pairs where the image is perfectly fine, but the caption is absolutely not informative. For instance, here we have this nice landscape, and then the caption that you get from the alt text is image not found. I mean, you don't want to train on this, an image not found. What you like to train on this image still is something like this generated caption, a green font with mountains reflected in. So the idea was, can you, like, so to speak, rescue a lot of these good images in Common Crawl that have bad captions, so we have overall more high quality data to train on. And then sort of like, without going into the details here, the short answer is yes. So this is again results the DataComp setup, x-axis ImageNet, y-axis average over the entire benchmark. This is just Lion style clip filtering in the bottom left here. You take the top 30% according to your clip model. And this is what we did with DataComp 1B. We also intersect with this ImageNet clustering. And these are all of the variants here that you get from either just straight synthetic captions, no filtering, only synthetic captions, or some combinations of synthetic and real captions. So what we found worked best was taking half of the data being captions as they appear in Common Crawl, and then the other half from an image capturing model. Back last year, we used BLIP2, but now there are better image capturing models like BLIP3 and so on. I think this is all very much worth revisiting. But I think the takeaway here is you do definitely see nice gains by bringing some of these images with low quality captions back. And I think there's a lot more to do here. I think others have also found this, like in the Lava paper. I think one of the nice key innovations was a creative way of captioning the images. Cool. How many minutes do we have left? 15 minutes. Okay, we have plenty of time. This is great. Then let me tell you a little bit more about what happened in DataComp over the past year since we put out this benchmark. So this is like the leaderboard on the website. Sorted by ImageNet and average accuracy over our entire benchmark suite. So this is what we started out with. The Lion 5B reproduction here, and then our improvement over that, the DataComp 1B dataset. And then one thing that was nice to see is that the community has already made quite a bit of progress here with better filtering methods. So back then, a year ago, we were about 30% on ImageNet for the medium scale here. And now the best method here, which is a combination of hype sampler and data filtering networks, gets 38%, so 8 percentage point improvement. And so what I'm going to do in the next couple of minutes is just tell you about how this data filtering method works. So the first and third row here are both based on DFN. And this is a paper that collaborators and I put out late last year. Specifically, this was Alex's internship project at Apple. So he interned at Apple with Vaishal, and sort of like Alex had just finished his work with DataComp, and then they could use this benchmark in order to push accuracies further up. Cool. And so like the high level motivation here was the following. That currently these data sets are constructed by taking a big web source, as we have said, Common Crawl often, and then you have sort of like a complex filtering pipeline, some model-based filtering, some heuristic, some rules that humans come with by hand. And then you have your data set in the end. And the question they asked here was, can we replace this entire middle step with a single neural network? So basically simplify this pipeline and just get all of the information, what is good, what we want to keep, and what is bad, into a single neural network. This is going to make our decisions for what data points to train on. So at a high level, how they did this is as follows. basically, we are going to train two different kinds of clip models. The first clip model is only focused on filtering. And the first model that's focused on filtering is trained on a much smaller, high-quality data set. So far, when we trained clip models in this talk, it was always at very large scale, right? We used all of Common Crawl, billions of images. And initially, when we did this in the context of Lion already, the hope was the following. Okay, we train a clip model on Common Crawl, we get some accuracy, we start to get better accuracies than the OpenAI model that we used. And this could be a really nice feedback loop, right? You get a better clip model, the better clip model becomes better at filtering. If we have a better filtering model, we can build an even better training set, then we have an even better clip model, we can use this for even better filtering and so on. The problem with this of like nice vision was it didn't work out at all. It turned out making the models better on ImageNet had no impact on their ability to do a better job at dataset filtering. And what Vaishal and Alex figured out here was that in order to train a model that's good for dataset filtering, you should ignore some of these downstream metrics like ImageNet. It's fine if the model is fully on ImageNet. The most important thing was training exclusively on high quality data. So when we train our final model at the end, we want to have a lot of data, and it's fine if some of the data is noisy. But for this data filtering network, you only want to train on high quality data. So this is the step one here. We train this data filtering network on some high quality data. They had it Apple internally. You can also use some public data sets. It's a little bit worse than it just had more high quality annotated data. And then you use this DFN model here that we just trained. And you now apply this to Common Crawl, basically to invest the entire web again. You do the split-based threshold filtering, and then we get our final training set. Cool. And then we can see how well does this work. So x-axis here is compute. Y-axis is ImageNet zero-shot accuracy. This is a nice way of visualizing is a method good because it uses a lot of compute, or because it's actually inherently better. And so we have 4 different lines here. The blue line is Lion, as I mentioned, it was the starting point for us for all of this. Then the red line is the compute versus performance trade-off you get from the OpenAI models. Orange line is what we got from DataComp 1B. And then the green line, this is DFN, data filtering network. So this is an even better compute trade-off. And back when we did this, this was the state-of-the-art public clip model, 84.4 zero-shot accuracy on ImageNet. Cool. Okay, so we'll have one last slide before we conclude. This is about something we just put on archive yesterday, so I thought I should tell you about it briefly because I'm very excited about this. Okay, all of this was about like how do we do rigorous data set design with a focus on multimodal data, because this is what I just knew about most and I wanted to understand in more detail. But once we had sort of like done this DataComp for clip training, the next obvious question was, okay, we have seen a lot of progress with better data set design for clip style models. What about other large models that people are training? The most obvious question was, what about language models? Can we use a similar process here with setting up a benchmark for data set design to also improve on language model planning? And the answer is yes. So this is DataComp LM, DataComp for language models. And these are, again, these plots, x-axis compute, y-axis performance. So we can understand what's the performance versus compute trade-off. And the orange line here is the data set we built as a baseline in this DataComp for language model spreadsheet. And then the nice thing here is that this is the best open data language model training set at the moment. So like outperforms others like C4, Dolma, FineWeb, and FineWeb-edu. And it reaches comparable performance to Llama 3, the 8 billion models, and Mistral, while being trained on less compute. So this model here is trained on 2.6 trillion tokens, while Llama 3, the 8 billion model, is trained on 15 trillion tokens. So overall, it's about factor 6x more compute efficient while getting roughly the same accuracy. So this is good. And I think this is just the starting point. Like we have some partial results that we can also do better data curation still for language models. So I think overall, this is a really rich space for research right now. Cool. Okay. So now we are at 30 minutes. Let's wrap up. Conclusions. I think if you had a synthetic data workshop, you're already on board with the statement here that data sets are a key driver of progress in AI. specifically in this talk seen this in multimodal learning. Clip is one prime example, the other one is text-guided image generation. Both of them rely on really large image text data sets. And as I mentioned, there's still a lot of room for improvement. So we had a lot of ideas that we still want to explore on the image text side. There's more stuff that you can do also on the language data side. And yeah, I'm very excited to see what the community comes up with here. Cool. And as I mentioned, the two projects we did here were Lion 5B and DataComp. And I am happy to take questions now. Thanks.
Thank you so much for the talk. I'm curious, you mentioned that the loop of checking InfinGen performance and filtering did not work that well. Do you have any intuition on why it's not a good proxy?
No, this is a great question. Yeah, I mean, in the end, I really don't know. I can't give you a like confident answer here. I mean, in the end, it's two different things, right? Like when we do ImageNet classification, we feed in an image and then we look at like the inner product with the class labels. If we do this like fully open world filtering here, we feed in an image and then the caption, and we hope that these scores correspond to training quality. But in the end, we don't really know what makes a good training data point to begin with. So this is, I think, why this is hard. I think there are lots of good questions for research here.
Question. The first question is that you use the clip model of the data building network to filter the data, but do you observe that this can, when you train the clip model, do you observe that your model will bias towards your filtering data because you use the high quality data for filtering and you use a clip model for filtering? If possible, that it's biased towards original model, and if observed this, how can you avoid that?
Yeah, this is a really good question, and this is something we were worried about. And so, like, I think there's a two-part answer. So, like, first of all, how do we know if this is happening or not? And so, like, one concern could be the following: like this DFN model that we used for filtering, that is actually fine-tuned on ImageNet because we observed that helps with classification. Okay, so maybe now when I tell you the ImageNet accuracy, we're only good on ImageNet and nowhere else. This is why I think it's important to evaluate these models widely on a wide range of downstream data sets. This is why we have about 40 of them. And so like, at least based on us evaluating the resulting model, this is not the case. Like the DFN trained model that does well on ImageNet also does well on many other downstream data sets. Like just one that comes to mind, Olga's group at Princeton has a nice data set for geographically diverse image classification, GeoD. And the DFN model that we trained here is also among this large testbed of clip models, state-of-the-art on GeoD. So I think the models do get broadly better, even though we maybe bias them somehow with the data filtering network, but I don't think the biasing is actually that strong. So maybe to get a little bit of my intuition across, I think there's a very big difference between training on data and then training on data that was filtered by another model trained on data. So like you can train on a data set A, and you can train on a data set A prime that was sort of like created by using a filtering model trained on A. And the second process has much less direct influence from A than the first process when we directly train on it.
My second question is that our observers in some sample you give for the image caption is pretty short captions. But if can you apply your model to a pretty long caption, and does it work or not?
So now for the, you mean for the image captioning work?
Like the DataComp.
The
sample is pretty short.
Oh, yeah. Okay, so great question. Yeah, I think overall web captions are pretty short to begin with. So if you look at image alt text pairs, the alt text is going to be pretty short. You are totally right that as you use this for filtering image text pairs with longer captions, the fact that the text encoder and clip models is actually not a great language model may become a bottleneck here. Yeah, would love to understand this in more detail, at least for these web data sources. It's fine, I think. If you now use this process for filtering longer captions, you'll probably run into the issue you mentioned. Yeah. Thanks.
Thank you for the talk. As I understand it, you're filtering away samples that are wrong, basically. Would it also make sense to filter away samples that are too easy or too hard?
Yeah, that's a good question. I think samples that are wrong, like there's a wide spectrum of things that are in the middle. I think that's the hard part, and you never quite know where to draw the line. Filtering away samples that are correct. Yes, this is what this TMARS paper does to some extent. You can interpret this paper here as filtering away image text pairs that are correct, but they are correct for an uninteresting reason from the perspective of image classification. So like, let's say you have a picture and then there's also some text in it, and then the caption is only the text. What you're primarily training then is OCR, optical character recognition. You're training the model to read the text in the image. This is maybe not what we want to do if we want to have like more broad image understanding skills. And so I think this is a nice example of what you were hinting at, that sometimes you also want to filter out at the upper end of the CLIP score, where the images are at some level correct, or image text pairs are at some level correct, but maybe not correct for the reason you want. Good question, thanks. I think this was the last question, correct? Cool, thank you.
Hello, is this working?
Did you connect the HDMI?
Oh yeah, I was just trying to figure out if the sound was broadcasting. Yeah, but we need the sound to broadcast this.
I think we have speaker. Yeah, Russ, I'm here. Can you hear me?
It's this. Hello?
Hello, yes, can you hear me? This is Russ.
Oh yeah.
Oh,
I
yeah,
think so.
yeah, I think it's working.
Yeah.
Oh, it's working.
Oh.
Russ, can you?
Oh
Okay,
yeah,
okay,
okay, perfect.
Is it working? Can you see me? Excellent. Yes, we.
Okay, perfect. Yeah. I'll share a screen.
Oh, let me share the screen. I can also share my screen.
All right, so thanks again to Professor Schmidt. So next up, we have Professor Ruslan Salakudinov, who's going to be presenting on data augmentation with diffusion models. So just to give a quick intro, Professor Salakudinov is a UPMC professor of computer science at the Department of Machine Learning at CMU and received his PhD in computer science from the University of Toronto. After spending 2 postdoc years at MIT, he joined U of T and later moved to CMU. And he's an action editor of the Journal of Machine Learning Research and also served as a director of AI research at Apple, as well as being a program co-chair for ICML in 2019 and a general chair for ICML 2024. He's a Sloan Research Fellow, a Microsoft Research Faculty Fellow, and a recipient of the Early Researcher Award, the Google Faculty Award, and NVIDIA's Pioneers of AI Award. So thank you, Professor, for being here. And yeah, thanks.
Thank you. Yeah, I apologize for not being able to be there in person. So I hope you can hear me and see the slides. Are the slides online? Everything is okay?
Yeah.
Okay.
yeah, if there are any issues, please let me know. But so today I wanted to talk about a couple of things. I'd like to spend half of the of the talk on the work that we've been doing together with my student Brandon Trebacco, as well as ecologists, and on effective data augmentation with diffusion models. And then the second part of the talk, I'd like to talk a little bit about what we call the visual web arena, a way of evaluating multimodal AI agents. And sort of the theme between these two talks is, the synthetic data augmentation, as well as building, simulators that would allow us to evaluate or would allow us to actually, improve one-shot or few-shot learning sort of settings. Okay, so let's jump into the first part of the talk. So we all know that data augmentation is a very effective tool, right? I mean, right now, when we're training these systems, we essentially do some form of pre-processing to the data, especially when we look at the visual representations, right? Such as horizontal flips, rand augment, sort of augmentations and changing the colors. Cut mix is another very popular approach where you're cutting, pasting some, parts of some images into other images to sort of create a diverse set of or expand your existing data sets. And any state-of-the-art systems today essentially are using those augmentation techniques. But obviously, we would like to build augmentations that are more adaptive to your data or the data that you're working with. And these types of augmentations also require some form of good intuition about your data, right? So you have to understand what your data is in order to be able to apply those augmentations. So ultimately, we'd like to build a model, and then there's a lot of work that's happening in that space right now. I'm listing a few examples where instead of doing these sort of, flipping or very sort of, like flipping images or changing the colors and such, we'd like to actually semantically change images. So for example, you're seeing in the image below, we have a train, but with the generative models, with diffusion models, we can actually generate, many different variations of the trains, right? And that can actually help you, as we show, improve your classification or detection systems by a substantial amount, especially if you're working in the space of a few shot sort of setting where you don't have a lot of training examples. Okay. And so the idea here is that we've been playing with is if you have a bunch of real images, can you generate these augmentations, right? That sort of have this semantic notion when you augment those images. And obviously one way of doing that is through the engine of diffusion models, right? And we'll talk a little bit about how we're going to do that. And one of the key ideas when we look at these augmentations is to use shared context, right? In the set of images to control what type of augmentation you want to apply. So let me give you an example. Let's say I give you one image of a cat, right? Well, we can rely on something that's called soft prompting or textual inversion system, where I say it's a photo of a Y, and Y is supposed to represent whatever is in the image. So we can essentially use the textual inversion to try to optimize what the representation of the Y should be. Right. And so in this case, the best representation we could have is a cat wearing a red bow tie, right? Because that's essentially what describes this specific image, right? So the token, once we fine tune the token, and again, the diffusion model here is fixed. So we're fine tuning the token Y, that would be representing a cat wearing a red bow tie. Now, if I give you another example, right, between these two images, you could probably say, well, there's something about red bow tie. If I give you another example, then you would definitely say that, Y here, the token Y that's common to all of these images and sort of generate all of those images or improve the maximizing log probability of generating those images would be a red bow tie. And if I give you, this fourth image, then the Y should be representing a bow tie, right? And so this notion is that given a few examples, you're hoping that this inversion of this representation of Y would capture some shared context across those images. And this is sort of the idea of if I give you a few images of a specific class, then you can learn what that soft representation of that class is, even though you might not know what it is. And that should help you then instantiate or generate multiple more variations of that class. And so here, the way that we doing this is we have a source image, and then we essentially, in this case, again, we're fine-tuning what the Y representation is. That's just a specific token that's randomly initialized. And, we go through the stable diffusion process, and we can control the augmentation extent with insertion steps. In practice, what we do actually is when we fine-tune the representation of the Y, we actually, cycle over different insertion steps. So whether it's a low, medium, or high, depending at which point you actually, fitting the model. Now, this is essentially, you can think of this as, again, as a soft textual inversion of a specific image. So here is the overall pipeline, right? We have a particular data set. We do the textual inversion for a specific class. For example, a class 3 might be a range of images, maybe not just a single images, but a few images. And then we're doing this augmentation by transforming this image into variation of the images. And then we train a downstream model. We're essentially mixing real data with synthetic data. And what we found is that, there are a few tweaks. There's a code that's available online, but we found that synthetically generated images are especially useful in the settings where you don't have a lot of labeled examples. Right, in the settings where you're sort of operating in this few shot setting domain. So we've looked at, these are just some instances where the image on the right is the original image, and then these are different variations, synthetic variations of that image. And again, there's nothing specific, there's no prompting that's we're doing. We're just basically saying a photo of a concept, and then we're learning what that concept is so that we can generate more instances of that concept. We've looked at, a few different data sets. We mainly focused on the few shot setting. We've looked at the common concepts. We looked at the fine-grained concepts. And we've also looked at a novel concept that we call leafy spurge. This actually was one of the motivation for this work was actually we started collaborating with ecologists. And I'll talk a little bit about this particular data set. And what's interesting about ecologists and botanists in their domain is that collecting data, very specific data of a specific concept, is very laborious and very expensive task. And so they can spend months collecting the data, and you have, on the order of a few hundred examples. So this notion of generating synthetic images from few examples in order to be able to train a better detection or classification model is actually very appealing in that domain. So I'll talk a little bit more about that. And so one question is, again, how much these augmentations improve classification. We were focusing primarily on classification, right? So we have some exemplary images, typically a few examples of a concept. We do textual inversion with a few tweaks, and then we generate synthetic images, and then we train a classifier on a mix of real and synthetic data. And these are just some results on a few different data sets. There is a number of baselines, also very good baseline. There's an excellent paper called Real Guidance, which also sort of uses a way of diffusion model to sort of, take the original image and inject some noise into that image, and works actually pretty well. But we do see that if you have this notion of shared context, right, and you're learning the soft embeddings, so the soft tokens, they can generate more variations. We can actually improve performance by quite a bit across many different data sets, right? And so when we looked at fine grain, we look at common visual concepts. In this setting, we actually get fairly strong improvement across different concept types. Of course, in this particular setting, as the number of labeled examples increases and you have enough examples of a particular concept, then maybe synthetic data might not help. But we do see substantial gains in the settings where we don't have a lot of examples. And as I've mentioned before, one of the motivation for us and the way they started this project is actually through collaboration with ecologists. And so let me just spend, a few minutes on this particular problem, because I think it's an interesting problem. It's a real world problem. So this is an example of something that's called leafy spurge. It's a problematic weed plant in North America. It's a problematic in the sense that it can grow and sort of destroy the natural habitat around. So it's fairly invasive plant. And when we talk to ecologists, they really care about detecting those plants so that they can go and control the local environment. It kind of looks like a nice plant, but it's actually very invasive. So it can destroy the natural sort of environment of other plants and as well as animals. And so we've surveyed about 40 sites, varied in land use, history, plant community composition. So, we worked with ecologists. Well, we didn't actually survey the site, the ecologists did. This was happening out of Montana. And this is just an example that, the botanists and ecologists, they basically spend a few months going around and searching for this plant. They typically, create these 10 by 10 meter plots. Then what they do is they fly the drone to essentially collect the data. And again, this is fairly laborious process. And then what they do is they basically take the drone images and they look at these quarters of approximately 3.5 meters by 3.5 meters. They subdivide them. They become 250 by 250 pixels. And then they go and manually label, this has spurge, this doesn't, this has, this doesn't. And so it's fairly laborious exercise. One interesting thing about the data is that this is what the real data looks like. And from 50 meters above the ground, because they're flying drones to try to detect those plants. And if you actually take the embeddings, the clip embedding of these images, and you look at line data set, and you look at the nearest neighbors in that space, you're sort of finding these plants. And we also tried looking at foundation models and GPT models and multimodal models to try to say, do the existing foundation models understand fairly precisely what these spurge images are, what that spurge plant is? And it's not very well defined in the sense that, there aren't a lot of examples of this plant on the web. And so it's very suitable for, studying questions like, for example, few-shot learning, right? Because these images are not part of training data sets or part of the training data when these large models are being trained. So it's an interesting kind of way of evaluating your models on something that's GPT-4 doesn't really understand or has a good visual understanding of what these plants are. And one of the things that, again, we're seeing gains, and even when we go beyond 16 examples, so here we've looked at 2, 4, 8, 16, but even when we go to on the order of 50, 100 examples, we'll still see gains compared to baselines such as doing random augments, standard augmentations, when we building classification models. The other interesting thing is that, you can also do things like you have the original generation, original model, you can add mountains, you can add snow, you can add grassland. So it sort of allows to semantically manipulate the images while still maintaining, the presence of spurge in this case, right? And that actually helps improve classification accuracy by quite a bit. We're also working on detection right now with ecologists, because what they ultimately want to do is they want to be able to fly the drone, detect those images, and basically automatically spray, and kill that specific weed. And, we also have a larger version of this data set that's released. So you're more than welcome to look at the data and see if you can improve either classification or detection of this plant. And it's actually, again, as I mentioned before, it's an interesting evaluation case because a lot of foundation models don't really work well out of the box and sort of like zero-shot setting when trying to identify this particular plant. And again, this is just, the data collection process. This is part of the release of the data. So you can kind of like see what the environment looks like and such. And so this fine scale classification will allow more effective management of leafy spurge in this particular case and responding to the outbreaks. And it's a fairly big deal for ecologists, right? And they were pretty amazed to see that, the synthetic generation allows them to improve classification accuracy in what they're looking at, and, will help them actually, act to find that plan. And just to give you an intuition is that there's a lot of interesting things like landscape change detection. They're looking at bare individual detection and retrieval. So there's a lot of interesting sort of data sets happening in that space that sort of goes beyond your standard kind of like image caption type of models. Okay, now this is sort of, now I want to switch gears a little bit and talk about, so far we've talked about, data augmentation, trying to generate synthetic images, with semantic variations in order to improve classification and detection. Now I'm going to focus on sort of building simulators, but simulators in the setting of multimodal agentic tasks, okay? So this is something that I'm really excited about. And then there's a lot of open questions about synthetic data generation, but also synthetic trajectory sort of generation, because as I mentioned before, getting the data is very laborious, much like what we've seen in a spurge setting. Okay. Now, I'm very much interested in autonomous agents, and a lot of productive tasks today can be performed by a computer, right? So there's a lot of opportunities to automate sort of routine tasks and augment human capabilities. So for example, how many of you have tried setting up AWA instance, right? My students are telling me that it's actually a really, really tough thing to do. And the question is, why can't I have an agent or an AI system that will go and set it up on my behalf, right? So just to give you a glimpse, this is something that we've been looking at. And again, this is sort of goes in the spirit of creating simulators. So let's say I give you the following task. Navigate to a page of a good Thai restaurant in Pittsburgh. It should have at least 200 reviews and 4.3 stars, and pick the one with the highest rating. Right, and this is an agent. This is an agent, which is the backbone of this agent is GPT-4. It sort of goes to Yelp. It tries to look at the restaurants in Pittsburgh. It finds essentially the one that satisfies my conditions, has 200 reviews, 4.3 stars rating, and finds a restaurant called Pusadi Garden. It's actually a pretty good restaurant in Pittsburgh, right? And it's all done autonomously. There is no interaction, like the browsing itself, it's all done by the agent. Well, I can give you the task, make a reservation for 2 people at the earliest days, use my name, JY, and a phone number, right? And so the agent goes to the Google, it searches for this specific restaurant for 2 people. It finds the date that's available, and actually sets, a confirmation, right? The confirmation actually sends the phone number and sets up a reservation, right? And now it's waiting for confirmation. Again, this is done completely autonomously. There's no involvement of a human. The agent just goes and does it on your behalf. Here's another one in the spirit of sort of multimodal agents. You can say, help me navigate to the shirt that has this on it, right? And you're not saying what this is, you sort of have to rely on images. And so again, the agent decides to go to Amazon and essentially finds a t-shirt with that particular object, right? Now, these are cherry-picked examples, but it does show you systems that can, potentially solve some of these tasks, which is pretty exciting. And so one environment, which is a very interesting environment that was developed at CMU. It's called Web Arena. It's one of the most realistic web environments at the moment. It's looking at different categories like shopping, Reddit, GitLab. It gets data from websites like Amazon and Reddit and so forth. One of the problems with this data set is that tasks are specifically designed to use just HTML. And dealing with HTML is really hard just because the representation that you get is not very good. And so we've been sort of focusing on building and tracking the progress of multimodal agents, right? And so we've designed what we call the visually grounded tasks to test the abilities of these agents to accomplish these tasks. So you have visual inputs and outputs, which allow for, a set of interesting type of tasks, right? We've looked at environments such as one-stop shop, which basically mimics Amazon, Reddit, as well as OS Class, which essentially mimics Craigslist. Right, so you have a web page, you have a task specification of what you need to do, and you want the LLM agent to go and accomplish the task on your behalf. Let me show you some examples. Again, this is all built in order to have a simulator so that we can test the abilities of these agents to accomplish these tasks. So for example, here's one of the tasks. I think we have on the order of about 1,000 tasks. This is just one task. Let's say I give you this bicycle and I ask you, find me this exact bike that's listed for $300 to $500. And post a comment offering $10 less than the asking price. So that's what you're asking the agent to do. Find the post with this bike and offer $10 less the asking price, right? And here's what the agent essentially has to do. It has to find this specific bike, right, that matches the description. That's the bike, and it has to, put the title, make a comment, and then essentially end up in this state. Right. So if you're actually ending up in this state, that a success becomes a success state. So here you sort of have to understand the visual representation. You have to understand what the task is. So obviously the multimodality is very important here. Here's another one, just to show you what the agent actually has to do. In this, say you have buy the cheapest color printer.
Professor, I think it cut out for a minute, about a minute, maybe.
Oh, I apologize.
So you might want to go back one slide.
Yes. I apologize. Is this better now? Can you hear me?
Yeah, it's good now.
Sorry about that. Sorry, it got cut off. So we've been building what we call Visual Web Arena, building and tracking the progress of multimodal agents. And we've designed visually grounded tasks to test the abilities of these agents to execute these interesting and unique tasks. So let me show you some examples of what these tasks are. We have on the order of 1,000 examples. So here's the task of, finding this bike that's listed for, $300 to $500, and you want to be able to put a comment offering $10 less than the asking price. So here's what the agent has to do, right? You're ending up on the web page. You go to the bike category. The agent has to, apply the correct thing. It has to find the correct bicycle. And then essentially it has to, put the comment as asking for, $10 less than the asking price. Right, so this is an example of an agent actually executing and understanding, visually grounding what the representation is, and then going and actually putting this comment. And I see the future where your agent is actually going to be negotiating prices on your behalf in the near future, right? I think that's coming. Here's another example. This is, more on sort of Amazon-like shopping. Buy me the cheapest color printer and send it to Emily's place as shown in the image. And if you look at the image, it's upside down, right? So the agent has to sort of understand that and perhaps rotate the image to get the address and buy the printer. And so what the agent has to do, it has to autonomously navigate to the printer category. It has to find the cheapest, printer. It has to fill in this form, right, based on the address that's in that image. And then it has to place the order, right? So you can sort of see it's a fairly complex task of visually understanding what the task is in the images, as well as, how to accomplish the task. Here's another one. This is more of an information seeking setting. This is more like a Reddit environment. So if I ask you, what is the 2022 total nominal GDP of the area that produced most sugarcane in the year of 2021 in billion, right? And so what you have to realize is that if you look at that particular image and you have to analyze the graph, you would quickly see that in 2021, Asia produced most sugarcane, not Brazil. And then you sort of have to go to Wikipedia to find what's the nominal GDP of Asia, right? And so you kind of, you have to understand what the image is saying, and then you essentially browse through and find the answer. Okay. And so how does this environment set up, right? And again, these are just, you can think of them as the data here is real, but the environment is synthetic, right? And so the environment itself is an MDP environment where you have states, observations, actions, and transitions. So observations here are web pages, plus you can also use HTML. We have a set of actions that the agent can execute. So something like clicking, typing, pressing, go to a specific URL, go back, go forward. So it's a fairly, type in a specific element text, typically when you're searching for something. And so you can sort of see that it's a fairly big action space, and the agent has to be smart enough to figure out what it needs to execute at any particular instance of a web page. And then we have a deterministic transition function. Given the state, the internal state of the simulator, and the action you take, you go to the next state, right? And the next state would generate the observation, which is the web page. So the web page is a sort of, you can think of them as, synthetically generated web pages based on the internal state of the simulator. And then we have a reward function. And you can think of reward function as basically telling us, if you've taken a set of actions and you ended up in a good state, what's the reward for being in that state? So it's just a way for us to identify, have you solved the task or have you not solved the task? When we've looked at the tasks, we actually got a bunch of master students who designed these tasks across these different websites. You can see that some tasks are easy, and in terms of reasoning difficulties, in terms of visual difficulty, and some tasks are very hard. And reasoning difficulty was basically how many steps we needed to take to solve the task. And visual difficulty was basically assessed by humans to sort of look at the images and say, okay, that looks like a hard image for me to parse, or I need to really look in the graphics and understand what's going on in order to be able to, complete my task. And these are just some examples of reward function. Of what we do here is that, we have multiple of them. So for example, we have exact match. If I'm asking you a particular task, if I give you a particular task and the answer is one specific answer, like what is the ISIN number of a company and so forth, there's only one number and you have to get it for me. You have things like must include. We also introduced, VQA type of evaluation. So for example, if I say add something like this, something what this man is wearing to my wish list as I'm shopping online, then, we're basically checking, is it a green shirt? Is it a polo shirt? Because it's a polo shirt and it's green. And so forth. So there's different ways of essentially building a reward function that allows us to say, have we successfully accomplished a task or not? Right? Now, let me spend a little bit of time of talking about LLMs and visual language agents, right? So there's been a lot of work on looking at text and HTML, but unfortunately, HTML is very cluttered with unnecessary information. There's a lot of confusing text and such. So instead, we've been focusing on visual language models. And looking at what's called set of marks representations, and which allows us essentially prompting over interactable elements, right? So you have a web page, and you can put you can put a box around each element with a specific ID, right? So the way that these models are working is that if you have an original web page, you get set of marks and text content out of it, and that goes into the LLM VLM agent, and the VLM agent essentially outputs a specific action, like clicking on number 31. Okay. Now, when we look at this particular task, what's interesting about these tasks is that the success rates of GPT models, just state-of-the-art models, is about 18%, 16 to 17%. Humans are actually close to 90% accuracy in terms of solving these tasks. I mean, we've asked grad students to solve these tasks, and maybe they're a little bit, better than the average humans. But it's still the gap between what agents can do and what humans can do is actually pretty large. One interesting thing is that when we've looked at the numbers by humans, when they perform these tasks, we couldn't quite figure out like why, we started looking, why is it not 100%? And it turns out that there's certain tasks that humans are really bad at. Like, for example, if I tell you, hey, find me the cheapest Toyota car, and offer 10% less than the asking price. What people typically do, they don't want to search every single Craigslist, looking for a Toyota car. They just kind of like look around, they find some car and say, okay, that's the one, and I'm going to offer 10% less, right? So obviously those are mistakes that humans do. And then occasionally humans forget to click on them, placing orders. So we're asking them to buy something, they do the task, and then they forget to place the order, and they just basically say, okay, I'm done. And obviously that's considered to be a mistake because they actually haven't placed the order. So certain things that humans are really bad at, I think agents will be able to solve with no problem. And so when we've looked at sort of, these, trying to understand where these agents fail, you can sort of see that, these numbers are pretty small. These are just text only or caption augmented. And when we look at, more advanced models, like we've looked at Gemini Pro, we've looked at GPT-4V and GPT-4o, these models hit about 16%, 17% accuracy. So they're still far away from human level performance, and it's exciting because it basically tells us these agents are much, much weaker than what humans can do. This is just one example. I wanted to show you an interesting example of a successful execution trajectory of GPT-4V, where the task is, I don't like the author of this image from one of the posts in F memes. Can you help me block them, right? And so the agent has to start at the home page. It has to search for that particular memes, has to go through the thing. It has to navigate to a particular forum. It has to find a user who posted that image. It has to go to the profile page, click the block button, and confirm the blocking, right? So you can sort of see that execution of a number of these steps is actually fairly challenging, right? This was just one successful trajectory that GPT-4 could do. But again, it's just a cherry-picked example. And a lot of other examples, it just doesn't do well, right? And so we think that this visual web arena is a step towards building these general purpose agents. The tasks are not very consequential for now, but even for these tasks, state-of-the-art agents can't really do much. Long-term goal is to automate productive and economically valuable tasks. And of course, I think that the multimodality becomes very, very important because many real-world tasks require visual grounding. So I think that becomes an important part in order to develop strong general agents, especially agents that can sort of understand, visually ground, and understand the representation that you're seeing on the web pages, as one example. Right now, common failure cases, and I'm almost done, is that models oscillate between two web pages. Sometimes they get stuck in the loop. Sometimes the agent does something and then undoes it. So there's a lot of sort of silly things that the agents are doing. One interesting thing on the visual processing, sometimes there is special reasoning. Like if you're asking what are the prices of the product in the first row, it gets confused. What do you mean by the first row, right? And things of that sort. And so just in terms of discussion, I think that this visual web arena is an interesting simulator that allows us to test these agents and also start trading these agents. And then we need to do a lot more to close the gap. Reasoning over long horizons. We started looking at the search. Search actually helps improve the accuracy of these models. And you need strong visual language models and such. And then just in terms of conclusion, just wanted to point out is that even for the task as agents, collecting human trajectories when humans actually execute is fairly expensive and laborious because you have to label a lot of things. It's an extremely laborious task. And we've been thinking very hard, how do we generate synthetic trajectories? How do we, build an agent that can generate synthetic trajectories, maybe validate what these trajectories are? There is some work on generating synthetic environments, like the environments that we've built right now. Visual Web Arena, it's a synthetic environment. It doesn't exist, it's a simulator. So building these simulators that can essentially help you build better agent is a very sort of promising area of research. And of course, you can think about fine-tuning, but there is no strong open source multimodal models yet for agentic tasks. So that's actually one of the big areas of hopefully we're going to have some open source models at fairly soon. And again, just this notion of using synthetic examples or synthetically generated examples I think it's a very promising area of research in building these simulators. I mean, at some point we'll have to rely on this just because it's much, much cheaper to generate those examples. And I'll stop here. And sorry, I've run a little bit over time, but if there are any questions, I can maybe answer a few questions. Thank you.
Thank you. Okay, yeah, I guess we can take a couple of questions. Okay. Repeat the question, please. Okay, yeah. I will.
Hi, I've read your first paper before. It's next to the SQL version live. And my question is, could you shed some light on classic augmentation techniques versus diffusion-based methods? Because your motivation is that diffusion facilitates more natural blending of augmentation. But I wonder if being natural really important for deep learning your network, because if it's better as it seems, why don't we just use synthetic images alone to train a model instead as a augmentation method? So my question is being natural really important for deep learning models? And follows it, I see that the figure 10 of the paper shows the comparison between your synthetic methods versus cutout and round-off methods. So I don't know if they are used in combinations or used as a different kind of method. But my question is synthetic images really better than classic augmentation method, because classic ones can be used on the fly and it's very, very efficient to use. But for synthetic images, we have to synthesize them first and do some tedious work to filter them to be used as a augmentation or pure synthetic data set. Because I have done some preliminary research on this topic, and I keep questioning myself about it. So it would be nice you can shed some light on it. Thank you.
Yeah, so I partially heard your question. I just maybe just let me understand. So you're asking is, do we really need to use neural networks or diffusion models to generate synthetic images as opposed to using some classical methods, right? Like, I mean, the way that I think about synthetic image generation and where we see the value is we saw the value, especially in the search data, where we actually semantically modify images, right? So where, for example, we can add the mountains, we can add the snow and things of that sort. And I think that the diffusion model allows us to generate a lot of these images very quickly. Now, if you have some domain knowledge about the environment, so maybe some of the classical ways of like specifically manipulating images in a specific way would work. It's just that I think that the diffusion models and, textual versions of these are generic tools. Which is, once you learn the once you learn the soft token representation of what's the meaning of the class, generating images from that class is actually fairly easy to do, right? And so at least we found that it actually helps us in a few shot setting, quite substantially without actually doing anything specific to any specific data set. We just did it across many different sets, whether it's a spurge type of a particular plant, or if it's common concepts, fine-grained concepts, and such. So I think it's general enough tool to generate these synthetic examples using neural networks. But of course, again, if you have some domain knowledge about the environment that you're looking at, then perhaps combining this with a specific classical methods for, generating synthetic images would work. This is just much more, I think this is just much more general.
Thank you for explanation. So do you see it as a method to improve over existing methods, or it's a
I think
better
so.
way other
Yes.
than them?
It's definitely a way, because, so for example, when we looked at the few shot setting, we actually use we actually use augmentations. We do the flipping, we do the rotations, and then on top of it, we also, we did the ablation where we don't do it, but then we for fair comparison. But ultimately, it's an addition to the existing sort of techniques for synthetically creating the data. Yep. Of course, it's more laborious,
Okay,
but you can semantically change, there's semantic variations that you can introduce that some of these techniques like random can't, right?
Yeah, and it could be a great way to like classification or detection in the wild to provide more semantic meanings for like closed word works. Thank you.
Yes, very good question. Thank you.
Feel free to come up to stage. I think we could.
Thank you, Professor. This is a great presentation. So I got a couple questions. I have not been successful on using the classical augmentations on training a lot of models, a lot of use cases we use. We have very limited data. I guess haven't really given the stable diffusion version, so definitely going to give it a try. Do you have any advice when it comes to how many, like percentage-wise from real images? We do have limited images, but for like just best practices, should we use like 50% of synthetic images, 70%, or it doesn't really matter? That's my first part of the question. The second one is, you touched a little bit on landscape change detection. Can you talk a little bit about that? Just like what kind of problem you're trying to solve and how you approach that problem? Thank you.
Yes, so let me just sort of quickly answer those questions. So when it comes down to, let me just, this is for the agent. So for synthetic generation, so we've tried a lot of things. We basically tried, it's an empirical question of how much real data you're mixing together with synthetic data. What we found is that I think that 50-50 worked best for us, and I think that's the number that we basically were using across. I think that's what my student Brandon was using across all of these data sets. So essentially using 50% of the true examples and 50% of the synthetic examples, but in a batch. So, you have a batch of 100 examples, 50 are real, 50 are synthetics. You get another batch of examples. Again, you get 50 real and you get 50 synthetic, but these 50 synthetics are different synthetic data sets, synthetic examples, right? So you can generate infinite number of synthetic examples, but when you're training your model to kind of, we always would keep it at 50-50. That's just one trick for training. And of course, like that's a number that can change. Maybe you want to do 30% real, 70% synthetic and such. But the important thing again for us is that we've actually generated a whole lot of synthetic examples. So every batch would see a new batch of synthetic examples. Right.
That makes sense. Thank you. Yep.
Yeah, and so for the landscape change detection, we haven't really done much work. We're just working with ecologists right now to try to figure out what their problem, what kind of problem they're trying to solve. I think that a lot of it is grounded to the health of the plant, and how, so what they do is they basically every few weeks, they take images and then they try to measure some form of the healthiness of plants in that specific domain, a specific environment, right? And so but unfortunately, we haven't really done any work in that space yet. So I can't really
Okay,
say
thank you.
much. Yeah, I think it's an interesting, and again, this is like very unique type of data that ecologists are creating, and I'm hoping we're working with this ranch, MPG ranch. Hopefully, they're going to be releasing some of that data, because data is fairly important to study these effects, and they're putting a lot of time and effort into building these data sets.
Absolutely. Thank you. Appreciate it.
Thank you.
Okay, I think we're probably at time, and let's thank Professor Ruslan Seleknov again, and I will.
Thank you.
Professor. And we'll take a 10-minute short break from here, and then we'll resume at 10:50. Still here? Yeah. Thanks, Professor. What is it?
Yeah, thanks. I hope everything. Sorry, sorry, like I know that I got cut off. I couldn't see it being cut off because internet on my side was working fine. So I didn't, thanks again for hosting me remotely.
No. Yeah, thank you again for joining. I think, yeah, overall it went really great. It's really a good talk.
Okay, thank you. I hope the audience was
Yeah,
happy. I hate to give remote talks. I apologize. It's just that it's couldn't quite make it.
Yeah, definitely looking forward to like seeing you in person next
Yeah,
year.
in-person talks are just much. Yeah.
Okay.
Thank you.
All right. Thank you. We'll see you.
See you.
Okay. All right. Yeah, so we need a sufficient amount of variability and diversity to make sure that we are capturing the whole distribution of the patterns that we want to recognize. It needs to be balanced. If the distribution is very skewed, then with the limitations of the current machine learning techniques, you know what's going to happen. The model will be biased. Domain relevance. Once you've captured very comprehensively the domain that you're capturing the data from, you want that distribution to match well to your target distribution where you will actually deploy the models. Label noise. If the label is very noisy and you train your model based on that using supervision, then the model will not perform well. The richness of the label is critical. Imagine like 20 years ago from now, in computer vision community, we had a single categorical label for image, and we were trying to solve the problems in that way. And we've come a long way, and think about all the other per pixel level information, depth, and all that is, all this information is so critical, and things will become more critical once we go beyond the categories and this, real numbers. But if with the emergence of a multimodal models, where we're training this text and, vision models together, the richness of the language is really critical to make great advances. Ethics and legal compliance, coming from industry, this is actually very critical. If you release a model and then there is some shady practice happened in the data side, it becomes a huge problem. So looking at all this, take a moment to think about, okay, let me build a new data set. Let's go out, I have a camera, and let's capture some patterns and let's label them. It becomes a pretty daunting task. So I think synthetic data has a lot of promise to address a lot of these challenges. Here's not my work, but a good colleague of mine back at Microsoft, they used a synthetic face images to build face recognition models. And these are very high fidelity. So why do we want to use this? It's very easy to control variation and diversity, especially if you're generating images with graphics pipeline. All this illumination, pose, geometries, you're all under control. Balanced distribution comes for free, of course, because you are the one who's generating it. And label, it must be clean, unless there is a bug in your graphics pipeline. Superhuman level richness. Really at the per pixel level, you know everything about the image. And these are not real humans, so no personal information. And it's possible to match your target distribution in this sense, like ethnicity or the background, the specific clothing that you want to optimize for. Yeah. All right, so we've come a long way in terms of generating this synthetic data. Nerve, I'm pretty sure everyone knows about it, Gaussian splatting, and I just picked up one recent work at this conference on generating human avatars. But it's not only about photorealistic rendering. There's simulators that we can use to study certain research areas where working with the real data is just very difficult. And of course, these large language models and multimodal models are opening new doors in the synthetic world. So in this theme of synthetic data, I'm going to present 3 projects where we use the synthetic data for some interesting applications. The first one we presented at ECCV in 2022. It's called Neural Sim. So the basic idea here is you generate data on demand for your given target domain. So think about test scenario 1. It comes with certain camera angles, certain illumination, certain zoom, camera configurations, and different test scenarios might have different distributions as well. So when we train a single model on the same domain, per different configurations like pose and zoom and illumination, you get, say 90%, near 90% accuracy. But then if you are training a model on a different domain and then deploy it, completely different pose configuration, the accuracy drops by 31%. And what we are proposing here is we can actually generate synthetic data optimized for your test scenario so that that lost accuracy gets back. So how do we do it? Oh, in case you're not familiar with nerves, here's a nice tutorial video that me and my colleague Daniel Wedge put together. It's just for fun. Go to YouTube, search "We Are the Nerds." He made this song, and I play the guitar on this. All right.
What's a nerve?
So how do we actually generate data on your target distribution? We formulate it as a bi-level optimization. So here's a pipeline. You start with certain rendering parameters. It gets into the nerve. We generate a training data set. You have your favorite model to solve your target problem. In this case, it was an object detection. So we are using RetinaNet. You train on the synthetic data. You validate on your validation set. You get certain validation score. So the goal here is optimize for these rendering parameters so that you minimize any loss value on your validation set. And to solve this, we decompose the problem into two sections. One is on the object detection part, and then the other one is the rendering part. And the loss function can be decomposed in this manner. So let's drill down into how we can actually solve this. So on this part, we are approximating it with a set number of images that the nerve pipeline will generate. Plug that back in, chain rule. We have these three terms for gradients. The first term is a second order derivative of the object detector that you're trying to optimize. The second term, the gradient of the rendered image with respect to the rendering parameters. And then the third is where we do the probabilistic sampling of the rendering parameters, the very first part. All right, whenever you hear probabilistic sampling and gradient together, what do you think about? It's there's no trivial solution to do this, but we have this tool, Gumbel Softmax. So we can, this is a continuous parameter space, right? It's a pose and all that. So we discretize this pose space into 8 equal-sized bins, as you see here. And then we use the Gumbel Softmax trick to approximate the sampling process. So we can compute the third term here. We have a second trick to make this really work. This is what we call twice forward and once backward. So think about how you would solve this. You would have to do a forward inference, and as you do it, and then you compute the gradient, and you have to store all these parameters. And it creates a huge computation graph, and you need a lot of memory. We can actually compute the third term first, and then do the autograd with the vectors that you computed to compute the gradient of the first and the second term here. This is what we call it. So to give you a detail, in the first step, we just do the forward pass, but then we don't store the gradients. This is just to render the images, which is required to compute the third term. And then we keep forwarding and backward. You get the gradient for the third term. We use that and then do a forwarding again through 1 and 2, but this time it's going to be efficient. The last trick that we use is to compute the first 2 terms, the 1 and 2. It's a still expensive process. When our intern Yunha was working on this, we had NVIDIA 2080 Ti, and he was complaining that, hey, I can't fit this on my GPU, even with very small image. And then we are thinking about how we can optimize this. So we can actually divide images into patches and then just do this in a patch-wise manner. You will be losing a long-term relationship there, but that's fine. So with these three tricks, we've started evaluating, okay, it looks like the pipeline is working. Let's start from some synthetic data to evaluate this method. So we took the YCV data set. It has a couple of objects. Started with synthetic setup where we are exactly controlling pose, zoom, and illumination. And the blue line represents our approach. And then the other colors are some no optimization and some baselines. So full overlap means there's no domain gap. No overlap means there is the largest domain gap. As you can see, by optimizing the rendered images for your target domain and therefore matching the distribution, you can see there is practically no difference in the distribution shift. Here's some numerical numbers. Yeah, across many object categories, it's showing some good performance. Next, okay, synthetic. All right, it works. Let's see how it performs on the real images. Similar story. So the NSO it's a the neural sim optimized version. NS is a neural sim, but we don't do this bi-level optimization. And as you can see, performance-wise, it's also performing pretty well. Here, we don't necessarily control all this pose, zoom, and illumination. These all come from the real-world characteristic of the data. Here are some actual rendered images. Here's some sample of the test distribution, and compared to some baselines where, sometimes pose isn't optimal, or illumination, you can see these black boxes. Whereas when we optimize it, gives pretty good images. I personally work on video, and okay, I pushed. All right, let's see in the video setup how this will perform, where you will see a lot more variation in the pose. Yeah, similar story, both in the 0 or few shot setting, and when we have just a very few training data, it all remains a competitive performance. So that's one project that we did for generating images for object detection. This is a recent project that we are doing, which is generating text data, very rich text descriptions given videos, and then trying to solve the activity understanding using these synthetic text labels. So the basic idea, any video human annotated data sets, they give you a snapshot information like, oh, the person is doing dribbling, without giving you any information about the scene, pose, objects in the scene. Maybe one data set will give you a VQA setup where is the ball in the scene, or what color of the tent is the person using, without giving you the whole picture. So what we are thinking here is, all right, given this limited snapshots of the information, let's generate extensive annotations, synthetic, using LLM, then use that to supervise our model. Yeah, so to motivate, think about baking bread, and you want to develop an AI model that can nail cooking scenarios, and you want it to do a very fine-grained recognition of activities. All right, think about what kind of labels we need. Oh, person is baking bread, and right now the person is preparing dough. In order to prepare dough, these are the sub-steps the person will be performing. Before starting to prepare dough, you need ingredients to be ready. And in order to know when the preparing dough step is finished, you need to know that the dough is risen twice as big. All this information, and think about you annotating these by hand. And for thousands of activity scenarios, this is a daunting task. So the community in video understanding community has been working on this for a while, and recognizing the lack of this comprehensive information, there have been a few approaches to solve this. One is the video narrations. So the person in the video, like YouTube, they talk while they are performing activities. So this forms a weak supervision. These are free, abundant, but they are noisy. Sometimes you talk, but then you don't really demonstrate. Sometimes you demonstrate, you don't talk. Sometimes there's a temporal gap. All this contributes to noise. The other is a knowledge base. Think about before LLM, we have a WikiHow and we have the OG knowledge bases. These are very well structured, very extensive, but these are not aligned to any particular video. This is just a web document. So you need a good way to link these two sources of information. And of course, manual annotation is promising to give the most clean, aligned, customized for your target application, but this is very difficult to scale. And then large language models came in. These are free, some of them. This gives infinite amount of data. You can get the output text to be structured. It can give you very extensive information because it memorizes, supposed to memorize lots of web documents. This is very aligned. You can customize it for your target application, but it hallucinates. So just to give you a flavor, I went to Meta AI page and asked it how to bake bread. And it gives very comprehensive step-by-step information. Then put a AI model hat and then start asking questions to LLM, giving limited information. All right, I see dough, flour, some objects, and consider I'm an object detector. These are the objects that I'm seeing, and infer what action I'm performing. And yeah, you are probably kneading your dough. And similar, I wear a scene detector, action recognition detector hat, and then start asking questions about something else. In all situations in this scenario, I was able to get a pretty reasonable answer. Then it gives us an idea, as long as we have these limited information, then probably we can get a very high quality text descriptions. And if you think about it, it's really like connecting the dot game when you are a little child. You have limited partial hints, and then, okay, you ask LLM to connect the dots, and you get the holistic view of what's going on in the video. So along this line, our group at FAIR, we recently released this Eagle for the Gold Step label, which is a very comprehensive hierarchical for labels for procedural activities. It gives a 3-tier level activity labels, goal, step, and sub-step. And at each step level, you have a category label, free-form text, and some metadata like whether this particular step itself is a procedural, is it relevant to achieving your goal, and some summary text, etc. And it expands into the granularity. So using this data set, in this work, we just used the text information here, which tells you what step you are in, and then manually defined some prompts. We are doing prompt engineering in this initial exploration under 5 categories that we believe will be very useful for human activity understanding. The first one is pre and post condition. This is about, in order to start this step, what kind of objects the model should expect to see. And towards the end of this step, what kind of states of the objects, for example, the model is expected to see. So this giving some implicit information about the temporal understanding of the video. The second is partonymic action hierarchy, where, you saw this already. Some of the information label already comes with sub-steps, but because this was a human annotation, it's not 100% complete. So for those segments where we don't have a further sub-steps, we ask LLMs, okay, given this temporal segment, what specific actions the model should expect to see? So this is giving that information. Third is a visual scene. Okay, consider you are pan frying eggy bread slice to golden brown, and then what kind of objects the model should expect to see. So it's going to give you that object level information. Reason for action. This one is interesting. So this is giving given a step. Why is the person performing the current step? Why is the person stirring and mixing ingredients on kitchenware to cook? So this is giving, if you're coming from a robotics community, perhaps you're familiar with this. This goal-oriented and goal-conditioned inference has been shown to provide good benefits to recognition models. So this is what we are providing. And synonyms and antonyms, if you're familiar with contrastive learning paradigm, there's a notion of positives and negatives. So this is exactly giving you that. So with these 5 knowledge categories that we are generating, we are training a simple model. Consider you have your favorite video model. You get some embedding out. And then on the text side, we are generating these new synthetic text using decoder LLM. In this work, we used Alama. And then you have, on one hand, the ground truth text, and the other hand, you have a synthetic text. You encode them using the same model. And the learning is essentially a contrastive learning. The Eagle for the goal step data set provides 3 tasks. And in this work, we focused on the goal step detection in an online setting. This is where, given a streaming data, a video data, you're supposed to provide a label for every frame. And compared to the basic baseline reported in the original paper of goal step, plus the captioning is, we are using La Villa, where given a video, it can generate text. Paraphrasing, given a video and some text labels, we use GPT to rephrase this text and use that as an extra supervision. And then ours that provides these 5 categories of information. And you can see a good performance boost on both the goal inference and step inference tasks. We also experimented this on UCook2 data set. This is pretty similar. You have the goal information, the recipe that you're making, and then the step information that exists as you see in this figure. And we get similar performance boost here. What's really interesting is, given these 5 categories that we really hand engineered, what are the contributions of each category? And we found that providing the reason for certain action was the single most contributing factor among many others. Hallucinations, we all know LLMs hallucinate, and we were extra careful in measuring any possible negative impact that it's giving to our model. So what we did here is we use an independent text video model to approximate the notion of groundability. How aligned are they? The text that it describes, the visual concepts, can they be grounded in the video? So we use the off-the-shelf model, compute the pairwise similarity, and then rank the similarity of all the LLM-generated text labels. And then when we train the same model with no synthetic data, or top 25 most similar synthetic data, bottom 25, and over threshold of 0, and below threshold of 0, you can see, and when we use all of them, in any of the settings, there's no setting that it actually hurts the model performance. And quite surprisingly, even if we include this supposedly non-groundable text, it's still providing good performance. So it's a bit puzzling. My theory is because of the task being online activity recognition, which is very challenging. If you think about it, you're giving a streaming data, and at every second you have to provide a label. So equipped with this context knowledge is, I think, really contributing to the performance here. All right, so that's about using synthetic text for procedural activity understanding. The last bit that I wanted to talk about is using simulation to study essentially a hypothesis testing. And this is precisely the causal discovery and reasoning. So let's talk first a bit about what is causality. You know the concept and the importance of the data in causality research. So in order to do the research in causality, you need the data that supports these three things, like discovering the latent causal mechanisms, what's causing what. And you need to be able to precisely know or control the interventions and then the outcome of it. And the confounders, which affects both the intervention and outcome, ideally, you need to know what are the confounders, and also you want to be able to control them so that you can test some hypotheses. And yeah, again, this is impossible to do with real-world data, although we, unless we discover the alternate universe, essentially. So in this work, we were using a AirSim simulator. If the internet works. So this is essentially a drone and driving simulator with very high fidelity graphics engine. It's based on Unreal. Because this is a graphics engine, you can get depth and segmentation masks and RGB. You can control the lighting. It's all based on the real physics engine. You can record lots of data, generate infinite amount of training data. And it has a basic notion of agency. It tries to avoid bumping to other cars. It gives you multi-view information about the scene. And quickly you will see, you can just plug in different domains, city, urban, suburban, or mountain. So we are using this driving simulator for this research, and stepping back in the causality research community, what kind of simulation engines that people are using? Back then, we had three most relevant work. And as you can see, these are great for precisely controlling, the variables, intervention, outcome, confounders. But it's missing the high fidelity that this very high quality simulation engine is providing. So what precisely does the simulator provide? You can record lots of data and you can log all the information, RGB, segmentation mask, depth, the positions of the cars at each and every frame, traffic signal states, and the cars will abide by the law, essentially. Weather state, if there's a heavy rain, then it affects how the driver is driving the car as well. And the great benefit of working with the simulation engine is it provides the notion of agency. So you only need to define the high-level scenarios, like vehicle A, start from this waypoint, go through these waypoints and stop on your target destination. And that's all you need to do. And then the rest, the model, the car will drive itself. When there's a traffic stop, then you stop. When there's a heavy rain, you will drive slowly, and then it will eventually get there. So this is a very convenient way of generating new data. If you want it, you can also control the low-level traffic behavior. By default, the cars will not bump into each other, but you can artificially generate an accident scenarios as well. And again, this notion of agency, I think, is critical in generating all this data quite efficiently. So using this simulation engine, we generated a data set called leader-follower data set. And in this setting, we have intervention, which is a leader. And then outcome, there's a follower. So the follower is trying to follow the lead. And then the traffic signal, we are using that as a confounder. So that means like when there's a red light, leader went far ahead, and then the follower will have to wait. Then their distance will be larger, and this confounder is affecting both in this way, intervention and outcomes. 10K episodes, 150 frames for each, and we're controlling some variables. And we have two tasks here. We want to predict the trajectory of the vehicles. And then we want to also classify, this is binary classification. Given the two cars, are they related to each other in a causal mechanism? We have some baseline results, not very interesting for the theme of this talk. All right, so yeah, these are the three projects that we've done over the years on using synthetic data for some interesting applications. I talked about how we can use synthetic image for object detection, synthetic text for activity understanding, and synthetic simulation engine for causality. With that, I'm ready to take questions.
Thanks here for the fantastic presentation. I really like the concept. One quick question about the first topic. So if I understand it correctly, so the basic concept is to optimize the entire network based on the accuracy of the test data. So does the optimization and the performance of the model depend on the qualitative attributes of the test data, like amount of test data, diversity, quality of the data itself, distribution of different classes, all those attributes?
Yeah, so the assumption here is you have access to a validation, so test data essentially, that matches your target distribution.
So it depends.
It does depend on it, yeah.
The better the test data, the better the model or
Right.
training data that you get. Thank you.
Yeah, thanks.
So my question was regarding having synthetic images during training. So something I noticed in some experiments we did was it reduces the performance, and some of the talks I attended also had that claim. So I wanted to know or learn from your experience what kind of trade-off lies between using real data versus using synthetic data versus using a mix of the two. And what's the kind of inflection point beyond which synthetic data starts hurting model performance, if at all? How much can we scale up? Just wanted to hear your thoughts about this.
Yeah, I think if you're asking that question maybe 10 years from now, then I'm hoping that the answer is none. But given the current limitations, like generating images sometimes, it's common sense stuff. I saw this tweet, what was it? Making business agreement, and then you have this, but you have 7 fingers on one hand and 2 fingers on the other hand, which doesn't make sense. So these little details, we're not there yet. So in that case, it will hurt. I think text is closer to where we want to be versus image, and video is far ahead, I think. So yeah, that photorealism, I think, especially in visual synthetic data, is difficult. Although in certain areas, I think we actually nailed like face and hand configuration based on the actual skeletal models, body as well. You can exactly control the weights and clothing, all that. But still, this is a difficult hair. If you're from a graphics community, this is known to be a very difficult problem to solve. Yeah.
And a follow-up question is, have you explored metrics that you can use to actually compare the two, to actually see the effect of synthetic data?
Yeah, interesting question. Rather indirect on the performance on your target task. We have like SSIM and all those metrics. They're good for certain use cases, but it doesn't really tell us how good these are. This is all relative, like using method A, method B. Oh, I got better score here, then maybe it's better, but it doesn't really answer how close are we to the actual visual scene. But yeah.
Thank you. Thank you for your talk. So one of the motivations in your talk for using synthetic data is balanced distribution of data. My question is, let's say in the space of complex tasks like self-driving, as you're covering today. First, I think the first question is, in terms of real sensors that we have already collected, how do we know what distribution of data do we have, especially in this era when we're collecting terabytes of data? Certainly, we can't just look through by our eyes. And then, because once we can identify which one's missing, then we can perhaps augment and supplement using the synthetic, right? But have you seen any work as to how to perhaps kind of more formally define the space of scenarios that these agents can encounter, and then in terms of that formalization, how the distribution, what kind of distribution that we have in the real data set?
I haven't seen the work, but I can provide my perspective. By balanced distribution, so the definition of it in my talk was, okay, imagine you have certain configurations. This can be a combination of a few variables, categories, etc. Having even distribution of the samples per configuration. That's what I meant by balanced distribution. Now, the real world, this oftentimes will not match the distribution of the real world data. Like how many times do we see accidents happening on the road? It's rare. Do we want to have our training data to match that distribution to build a robust model? That's another question. And in my perspective, especially in the safety critical scenarios, we don't have to match your target distribution. Rather, having some balanced distribution for model development so that we can precisely study, okay, in these certain scenarios, even though the distribution is even, can the model reliably detect these safety critical scenarios? I think for development purposes, that seems more reasonable to me. But yeah, I think it's an open question. Yeah. Very good. All right. Thanks, everyone.
Thank you, Dr. Yeltsin, for the great talk.
Hello. The one times is not.
Hello, hello. Can people hear me?
Hello. Yeah. Nice.
Okay, it's probably gonna be back.
Yeah,
in a
probably
minute.
I'll do those.
Thanks.
So our next speaker is Professor Jadin, and Professor Jadin is an associate professor of computer science at Princeton University. His research focuses on computer vision and machine learning. He received his PhD from Princeton University and his Bachelor of Engineering from Tsinghua University, both in computer science. And he's a recipient of the Sloan Research Fellowship, the NSF Career Award, the Honor Young Investigator Award, and the ICCV MARC Prize, and 2 ECCV Best Paper Awards. So please welcome Professor Jadin.
Thank you. Good morning, everybody. Today I'd like to talk about our work toward an ImageNet moment for synthetic data. So I think many of you may have heard this phrase, the ImageNet moment of something, in particular computer vision. What it usually refers to is the demonstration of a powerful recipe, right, that combines lots of labeled data, giant deep networks, and lots of GPUs. And we know that this recipe can produce very powerful results. I would actually argue that the ImageNet moment has not arrived for all of computer vision. It has only arrived, by and large, for object recognition. It's because for object recognition, we actually have all the ingredients of this recipe. In particular, we have lots of labeled data, that's images and labels about objects. And I would argue that the ImageNet moment has not arrived for a substantial part of computer vision, particularly 3D vision. This is because we are missing one ingredient of this recipe. That's lots of labeled data. In particular, we'd like to have lots of images, and there are 3D annotations. For example, a canonical task in 3D vision is image to depth. Here, we'd like to have depths estimated for every single pixel. And to do that, if you want to employ this recipe, we'd like to have ground truth depth values for all these pixels. But unfortunately, getting this ground truth is actually very difficult, right? So the practical way of getting this for real world images would be depth sensors. However, we know that they have all sorts of limitations. First of all, it's very tedious to use them to collect data because you have to have a depth sensor with you while you're taking the photo. And second, the depth sensors actually have limited range. Often outside a certain distance, you will not get depth values back. And also the resolution will be much lower. And they don't work on certain surfaces, especially specular or transparent surfaces. So they don't actually give us lots of annotations we want. Now, what are the alternatives? Well, one of the promising directions is to use synthetic data. So here, I define synthetic data as data generated by conventional computer graphics. I think this is an important point to clarify nowadays because the term synthetic data has taken new meanings. That is, data generated by AI models. So here I'm specifically only referring to synthetic data generated by conventional computer graphics. Because we're doing conventional computer graphics, it's easy to generate limited quality with high quality labels. So this, of course, using computer graphics-based data is not new in computer vision, right? So for certain tasks like optical flow, a lot of training and tests is done on synthetic data. For example, this is the MPI Sintel data set is well known for optical flow. Synthetic data is promising because it has proven to be effective for a lot of 3D vision tasks. We do have 3D vision systems that are trained entirely on synthetic data and work well on real images. Certainly examples from my own work, including optical flow and depths from stereo. Now, I want to just emphasize a little bit more about using old-fashioned graphics. All right, so why insist on that? Why not just use synthetic data generated by AI models? There are multiple reasons without going into the philosophical ones. So one reason is that we want high-quality 3D ground truth that we can trust. And generation through neural networks simply is not known, at least yet, to provide this. Okay, so at least for now, we want to use physics-based simulation to provide reliable ground truth. Now, there are questions about using synthetic data. One of them is the domain gap, right? So this is a well-known synthetic data set, flying chair 3D. They don't really look like real-world images. So would this be a huge barrier to using synthetic data? I think at the fundamental level, the answer is no, because I believe there is no fundamental technology barrier in terms of minimizing or bring the domain gap to zero, because Hollywood has shown how to do this. We have all the tools we need to produce arbitrarily high photorealism. It's only a matter of cost. So in some sense, this is like an engineering problem. That said, the existing synthetic data we do have access to has a lot of limitations. So they do have limited details and realism, and they do have limited coverage of objects and things in the world. We don't have as much as we want, and the type of labels we have is limited, and also they are limited in terms of accessibility. For example, sometimes if you want not just the images and labels, and you want the underlying 3D assets, it's actually not available to you. Now, what can we do to address these limitations? So one approach is to take an approach like ImageNet. The ImageNet collected images from the internet, and similarly, we could collect 3D models from the internet. And actually, people who have done excellent work in this direction. For example, we have ShapeNet, we have Objectverse, and they have been used in a lot of works. However, this approach does suffer from some limitations. The fundamental reason is that creating 3D models is much harder than taking photos. So everybody can have a phone and snap some photos, right? It takes no effort. However, to create a 3D model, it usually involves a lot of human effort. Some human artist has to spend a lot of time to create a high-quality 3D model. As a result, we actually have a limited quantity of 3D models that you can download from the internet. And a lot of them are objects and not the full scenes. And also often a model you get from the internet you have limited control over it. For example, it's just a static mesh. If you want to rig it for animation, and you have to do extra work. Now, in this talk, I'd like to show you a new approach that's different from this ImageNet like approach. And we hope to achieve unlimited quantity, and we hope to cover both objects and scenes, and we hope to offer fine-grained control of all the assets that we can provide. So now I'm going to play a video that introduces this project. was actually introduced last year's CVPR, but there was some new stuff this year as well, which I'm talking about. In a nutshell, InfinGen is a generator of infinite synthetic data. It's not a static data set. So we can actually think of it as a generative model, except that there's no AI within it. Okay, so you can give it some random seed as input with optional user controls, and then it will allow you to sample random scenes that are in 3D. So here to know that this is not just rendered images, you actually have access to the underlying 3D models. And the key defining feature of InfinGen is that it's 100% procedural. Procedural means that it's generated from scratch using randomized mathematical rules. I'd like to emphasize that everything is procedural, from shape, textures, material to lighting, arrangement, animations. So basically, there's no external static data assets. So there's no, so every single mesh, every single material, the large structures, small details, they are all from mathematical rules. And then there is no neural network weights in it. So in other words, there's no mysterious arrays of numbers that you don't understand. I'll just give an example. Let's say we'd like to generate a tree, right? We write rules to randomize the branching and to simulate the growth. And now we have the stem and the branches of the tree, and then we can also apply materials that's procedural as well, and then we can have sub generators that also generate leaves, flowers, and fruits. And then in the system, we have high-level parameters that are exposed to users, which you can control, like height, the frequency of branch, density of leaves, and then there are also low-level randomness, which is the exact branch length and angles, and there's this displacement of pixels, vertices in the geometry, right? Angles of the leaf. All these are also have a lot of randomness internally, and this is built upon decades of computer graphics research, in particular Blender, which is an open source graphics tool that provides a lot of primitives that we can build upon. So that's a major enabling technology for us. And in particular, in 2021, Blender introduced the system called geometric nodes. It's essentially a graphic interface for you to write mathematical functions for procedural assets. So it's very user-friendly, so people who don't know programming can also do it. So think of it as like a PyTorch. In PyTorch, you compose basically mathematical functions, right? These modules together to form a compute graph that defines your network. Here, you form a computer graph. Yes, through this graphical interface, you drag and drop the modules, mathematical modules, and then this will define either shape, material, or lighting. So everything can be expressed as mathematical functions. And in our system, we have a transpiler that can take these graphs, this compute graphs created by artists or anyone else, and convert them into Python code. So you can actually do more flexible things with it, like adding loops, like adding recursion. With this transpiler, we can actually take open source contributions. Anyone can create computer graphs, and then we can incorporate it into the system. And here an example is the clouds in the background. And InfinGen has broad coverage of the natural world. Here's just a sample of the procedural generators we have. We have plants, we have trees, we also have system for creatures, and we have rigging for the animals. And so we have, the skin is done by cloth simulation. And we have a terrain system that's procedural. We have different materials that's also procedural. And the scene is generated procedurally. So we first procedurally generate the course layout, and then we place detailed assets, and then we do the rendering to have the images, videos. Okay, so that's what the system is about. Now, you probably have some questions about the system, right? So basically, this is all built from handcrafted mathematical rules. Now, one thing you might wonder is that, would it take forever to have good coverage, right? So for a good synthetic data set or data generator, we should have good diversity that matches complexity of the real world, right? How can we hope to achieve that even in principle? Okay, so I believe this is possible because because the world is compositional. So you might think that to develop different generators, we have to sort of do it one by one. So there's a tree generator, someone needs to write a tree generator, and someone else needs to write a bush generator, and then someone else needs to handle creatures. And all these should be sort of disjoint efforts in parallel. But in reality, there are a lot of subcomponents that can be reused, right? That makes the compositional system. For example, the bush generator can reuse the branching generator of trees, and the leaves can be reused. And for creatures, they share some lower level utilities. And for creatures, we have the rigging system which can in turn be applied to the tree generator and bush generators as well. So the basic point is that for procedural generation, we actually have composition, which allows exponential growth of complexity. So once we add a new generator, like say a new texture generator, this texture generator can be applied to all the existing generators, existing shape generators. So we have this sort of product of complexity that's exponentially growing. You can contrast this in sort of the InfinGen-like approach, right? So you add individual 3D models into your collection. So in this case, the complexity is actually growing linearly, right? With the number of data points you have. You add a new image, it doesn't impact your existing images. So because of this reason, we believe that as we add more generators, we're going to have this exponential growth of diversity. And at some point, this diversity will be high enough to be useful for lots of tasks. Of course, it might not match the real world complexity, but we might not need that to be useful. Another question you might have is that, okay, it looks somewhat photorealistic, but it's still not the same as the real world, right? How do you hope to match the real sort of, how close should it resemble the real world, or is it possible to do that? The answer we have is that we wanted the distribution to be somewhat close, but it doesn't need to be completely faithful. So for example, let's say we have the set of 2D points that represent the real world images. Look at this dragon image. Clearly, it doesn't exist in the real world. Okay, so it's a synthetic one, but your vision system has no problem dealing with it. Okay, so this suggests that the actual distribution your vision system can handle actually is probably is an envelope. It's a larger set than real world images, and so this suggests that it could be sufficient to just approximate this envelope, which would be sort of engineering-wise easier as well and more tractable. And another point is that often we might want to customize your distribution to the particular application. You might have particular constraints in your application, and which the system allows you to customize. You might want corals only in water, right? And so in this case, it's a procedural rule that you can specify. And we started this project with natural scenes because there are a lot of applications that are connected to natural scenes and objects. And also, a fact is that the vision system of humans and animals evolved entirely in nature. So to acquire a lot of intelligence of animals, and it's not necessary to be exposed to artificial objects. Okay, because everything's procedural based on old-fashioned graphics, we can easily get high-quality labels like depth, segmentation, and 3D boxes. And you can customize it as however you want. For example, if you're really interested in the little segmentation of these very tiny flower petals, you can actually do that in the system. Basically, you can you know how each pixel is generated exactly, so you can get all the information you want about this about any pixel. Right? So this is just a sample of possible annotations, but of course you can do more. And also, we insist on having real geometry, not fake geometry, that's often used in games or real-time conscious applications. So, for example, we don't use, like say, things like transparency or techniques that fake geometry, create an illusion of texture, right? Because we want actual accurate 3D ground truth. And then also we make sure that the system is efficient. We use the adaptive meshes, meaning that the face is closer to the camera. The resolution will adapt to the distance of the object to the camera. And so we can place the data generated by InfinGen in the context of other data sets, right? So there's this y-axis that tells you how much information you can get for each pixel, and then the x-axis is the kind of coverage diversity. So image data is kind of very diverse, have a good coverage. However, the information you get from each image is very limited. So you can have other data sets that provide more information about each image. And here, InfinGen right now, it doesn't have as much coverage as ImageNet, but the amount of information you can get from each pixel is much richer. And another important point is that InfinGen is free and open source, is under BSD license. And so anyone can use it freely to generate unlimited synthetic data. And here, the important implication is that data generation is 100% controllable and transparent. So before, we train a model by taking some data set and we write some code with some learning algorithm, right? We give both to the GPU and then we get a model. So you usually don't have as much control over the data because somebody else collected, and it's a huge data set, you might know what exactly it meant. However, with procedural generation, data is actually now code. If you're using InfinGen, you know exactly what's in your data set because you have full control of the procedural rules. You can inspect it and you can customize, you can optimize it for particular applications. Now, there is some computation cost in generating synthetic data because you do need to create the 3D models, you need to render them. And right now, this is sort of the current stats. We're hoping to further improve it. It's kind of expensive, but also, it's embarrassingly parallel. Also, we're optimistic that NVIDIA will solve all the problems. And so, if you want to just create a simple thing, it's not hard. We have Hello World, and which you can try. You can work on your laptop. You just take 10 minutes of CPU and 16 gigabytes of RAM. So with the natural objects, we generate some data. We tried stereo matching. And it turns out to improve the accuracy of natural objects by quite a bit. Although because it doesn't have any artificial objects on those categories, it doesn't work as well as existing data sets. But that's something we're going to fix in a few slides. Now, there is a large design space of using InfinGen, and then this is still very early. So we're hoping that we can by using this system there can be so we can help some vision tasks to have large improvements like ImageNet had for object recognition. And so people have started to do some interesting things. For example, people have cooked a large language model with InfinGen, where the large language model outputs the code, causing basically InfinGen APIs to generate 3D scenes. Of course, there are other interesting things that you can do. Okay, so I would like to also share some more progress about the latest. So we're working actively to try to expand its coverage of the world. And so this year we expanded the coverage from natural objects to indoor scenes. So this is this year's CVP, this conference, and we have a poster on Friday. And so this is a sample of the generated indoor rooms. There were different kinds of rooms, from living rooms to bathrooms to kitchens, and then we also have all these furniture and indoor objects placed. And then we can actually export the generated 3D scenes to real-time simulators. This is Unreal. And so if you care about real-time simulation, for example, for embodied AI, you can also use our system to generate assets. And we have released the code for InfinGen Indoors, and then this is a hello world example that you can try. Just a sample of the procedural generators we have occurring in the system. Right? You can see that there are different kinds of furnitures and also objects that you commonly see in the room. And one point is that we actually reuse a lot of our nature generators in creating these indoor scenes. For example, because we have a terrain system, right? We can have an ocean view outside the window, and we can place plants into pots to make them potted plants. We can take corals and put them on shelves to make them trinkets. One actually innovation of the system is that we actually have to address the sort of particular requirements for indoor scene generation, because indoor scenes are often very structured, unlike natural scenes. You can just scatter objects randomly and they look fine. So if you want, like say, a very tidy room with objects arranged neatly, you need to do we need to sort of provide this functionality. So this is a constraint system where there's domain-specific language for a user to specify the constraints about the object placement in the room. And then there will be there is a solver that will try to arrange the objects to satisfy these constraints. And so this basically decouples specifications from implementation. So here's a list of the predicates that you could use. So for example, you could say you want a certain number of shelves on the floor and on the wall, and then you want a certain number of tables, and the tables should be on the floor. You could also say, well, the chairs should be arranged symmetrically around the table, and then they should be facing the tables, and these can all be customized, right? You can have or not have these constraints. It's up to you. And then there we have a constraint solver that will basically do simulated annealing to try to satisfy these constraints. And we have a room layout system that's entirely procedural and can generate room layouts for multiple floors. And then given the rooms, and we can place objects. And so here's some examples. And then you can sort of use this constraint language to do custom kind of indoor scenes. For example, this is you can do a warehouse. You just need to write a few lines of constraints here. You will say, we'd like to pack the shelves as much as possible. And so we can, this shows sort of the flexibility of the system. InfinGen is currently being actively developed. We're still trying to expand the coverage and improve the quality and the usability, right? So we'd like to make it very easy to use for computer vision researchers, robotics researchers, and also artists or researchers who are interested in content creation. And now I'd like to acknowledge the team members. It's a large amount of effort. So for these are the team for InfinGen Nature, and then this is the team for InfinGen Indoors. And we have a poster on Friday morning, and please come to our poster if you want to know more details. And with that, I'd like to conclude my talk and take questions. Thank you. Yes. Yes, that would be the natural next step.
Yeah, I curious when you had mentioned Hollywood as a reference for
Yeah, I think the main issue is that we have a system that's expressive enough, but for something to look super realistic, you have to find the right parameters. So like, for example, if you want the skin of a tree, like the bark, to look exactly like something real, you would need to know the parameter is somewhere in the space, but you have to find it. Usually, in Hollywood production, from my knowledge, is that the artists need to spend a lot of time to fine tune these parameters to make them look visually good. So that will be the gap. So actually it's an interesting question whether how much this matters in terms of training a 3D vision system, because the training vision system you kind of it's sometimes helpful to enlarge the distribution a bit, right? So have some domain randomization to make the system more robust.
Thank you.
Right. So one of the goals is to make it super easy for your use case. Right now it's not quite there yet, but this is something we're trying to actively improve. I think there's fundamentally we can get to a point where you want a car, right, and then it's literally a few lines of Python code. Once you've installed the system. Yeah, I mean that's possible. I mean that's kind of complementary to InfinGen. It'd be easy for someone to do this if they want to. So this is this is something that essentially you can sort of add some procedural components to existing 3D models. Although it might not be a straightforward process because existing models you may not know how to exactly decompose it because such information is not available. But if it is, you can still sort of combine in some way with the InfinGen system to do that. But the trade-off is that for these parts, right, you still don't have as much flexibility or diversity
as it. So it sort of depends on your particular application, your requirements of the randomization.
So we do know that for certain tasks that having synthetic data helps, and that we have shown, like for example, stereo vision, boundary detection, and shadow removal. These. So right now, these we don't have the complete curve. It's like scale to the to like a very large set and see what happens with very large models. But that's something that we're hoping to like that.
It's like because you generate these videos, and the videos many redundant. I create them.
Right.
And training with those videos man quickly reach upper bound. And then you as for you.
Right.
So do you have some as regarding what kind of combination you generate actually if right.
Right. Actually, I think you bring up a very good point. Is that with sort of training very large models with lots of data, often actually compute will become a bottleneck. So like before data becomes bottleneck, right? But that's also an advantage of a procedural system, which is that because you can 100% customize your data set. So there is a large space of you can basically ask this question, like given my finite compute budget, it can be enormous budget. How should what kind of data would give me the best performance? And InfinGen provides the flexibility for you to do that, right? Because with a static data set, all you can do is to select which image to include. But for InfinGen, you can actually change, everything. So this, I think this is an interesting research question. I don't have the answer, but I'm confident that the sort of a good configuration is in that space. But we need to search for it and find out. Thank you, everyone.
Thank you, Professor.